In this chapter, we'll learn practical methods for evaluating AI systems, how to measure performance, robustness, fairness, and safety. We'll introduce the key metrics, test designs, and how to interpret results so you can judge model quality confidently. A model is only useful if it meets the needs of the system you're building. Apply the automatic evaluation methods from Chapter 3, but always judge results against your application's specific goals, constraints, and failure modes. This chapter has 3 parts. First, we introduce the evaluation criteria you'll use and show precisely how each one is defined and calculated. Then we apply those definitions to concrete concerns. For example, how to detect factual inconsistency, hallucinations, and how to measure domain skills like math, science, reasoning, and summarization. With dozens of foundation models and thousands of benchmarks, selection can feel overwhelming. Check each benchmark's tasks, data sources, metrics, and evaluation protocols, and be wary of aggregated leaderboards that can hide trade-offs. Practical rule: pick benchmarks aligned to your use case. Run several targeted evaluations, and always validate top candidates on your own representative data. The model landscape now includes both proprietary offerings and a growing set of open-source models. Teams repeatedly face the decision to self-host models or call a hosted model API, and that choice has become more nuanced as API providers build services on top of open-source models, blurring the line between hosting and using a hosted service. This final part shows how to design an evaluation pipeline that guides your application's development over time. It brings together techniques from the book to measure performance, compare alternatives, and prioritize improvements for real-world use. In this section, we'll define the criteria used to evaluate solutions. I'll explain each criterion, why it matters, and how we'll apply them consistently. A deployed application that you can evaluate creates more harm than one that was never released. It still costs time and money to maintain, but you don't know if it's working or if removing it will cause more expense. At conferences, I've found most people agree. Lack of observability is the bigger problem. Many AI features get adopted by users, but their business value is unknown because teams lack measurement and visibility. For example, a used car dealer deployed a price prediction model, but never monitored whether its estimates were accurate, so engineers had no way to judge its value. Likewise, after the ChatGPT wave, many companies rushed to add support chatbots and still can't tell if those bots improve or degrade customer experience. Before investing time and resources, decide how the application will be evaluated. Evaluation-driven development borrows from test-driven development. Define clear, measurable evaluation criteria before you build. This focuses development on what matters and reduces wasted effort. This section introduces evaluation-driven development, an approach that starts from concrete evaluation criteria to shape design and iteration. We'll define the concept, explain why measurable evaluation matters, and show how it guides development choices. Even when new technologies attract attention, enterprise decisions are driven by return on investment, not buzz. Applications get deployed only if they can demonstrate measurable value using concrete evaluation criteria. So the ones you commonly see in production are those with clear metrics and outcomes. This brief overview highlights the central idea you're about to study and why it matters. Keep that goal in mind as we work through the steps and examples that follow. Recommender systems are popular because their success is directly measurable. Firms can observe whether recommendations raise user engagement or purchase-through rates. That clear, business-facing metric makes it easy to test, compare, and iterate recommendation models. When you face a difficult problem, split it into independent, simpler subproblems you can solve one at a time. This reduces cognitive load, makes debugging easier, and often reveals reusable patterns. A practical way to evaluate a fraud detection system is the amount of fraud loss it prevents. In other words, money saved. Be sure this calculation nets out recovered losses, the cost of investigations and false positives, and any customer impact costs so you measure the real benefit. The single dash shows that explanatory prose is missing here. Replace it with a short paragraph that states the main point, gives one supporting detail, and points the viewer to the next idea or action. Coding is a special generative AI task because the output can actually be executed and tested. That lets us measure success objectively, for example with unit tests, sample inputs, /outputs, or program invariants, and use failing tests to drive fixes and improvements. Display a short, clear phrase that captures the main point, then explain the details verbally. This prevents clutter, keeps viewers focused, and lets you add nuance without overloading the slide. Foundation models are general purpose, yet many applications are closed-ended. Think intent classification, sentiment analysis, or next action prediction. Those tasks are easier to evaluate because they have clear labels and can use automatic metrics, unlike open-ended generation, which often needs human judgment. Evaluation-driven development favors projects with clear, measurable outcomes because they're easier to justify. That's like searching for a lost key under a lamppost. Convenient, but not comprehensive. Many potentially game-changing applications lack simple metrics and get overlooked. In practice, moving models from prototype to production stalls because we don't have trustworthy, repeatable ways to measure real-world performance. Building robust evaluation pipelines removes that bottleneck and lets teams confidently deploy and scale many applications they currently avoid. Start every AI project by listing evaluation criteria tied to the app's goals. Group checks into 4 buckets. Domain-specific capability. Does it solve the core task? Generation capability. Are outputs fluent and correct? Instruction following capability. Does it obey prompts and guardrails? And cost and latency. Are inference cost and response time acceptable? When you ask a model to summarize a legal contract, you need several different metrics. Domain-specific metrics measure legal understanding. Generation metrics check coherence and faithfulness. Instruction following ensures the requested format and length, and cost/latency tell you the money and waiting time trade-offs. Now we flip the perspective. Rather than asking what a given approach can evaluate, we start with a criterion and ask which methods can measure it. I'll show common mappings from criterion to approach and highlight the trade-offs you should expect when a method only partially captures the criterion. In this section, we'll define what a domain-specific capability is and why it matters. We'll focus on how specialized knowledge, tools, or models allow systems to perform much better on narrow tasks than general-purpose ones. A model's ability to perform a task comes from its configuration, architecture, size, and, crucially, its training data. If the model never saw Latin or never learned to generate code during training, it won't understand Latin or write code reliably. So choose a model whose data and setup match your application. To know if a model really has the capabilities you need, evaluate it on relevant domain-specific benchmarks. Thousands of public benchmarks exist for tasks like code generation, debugging, math, science, reasoning, legal knowledge, tool use, and games, and you can also use private, task-specific suites. We often judge models by functional correctness, but that's only one axis. A generated program or SQL query can be technically correct, yet unusable if it runs too slowly or uses too much memory. So we also need to evaluate efficiency and cost for real-world use. Efficiency is measured by concrete resources like runtime and memory, not just whether the query returns the right results. BRD SQL, Lee et al., 2023, scores models on execution accuracy and on efficiency by directly comparing the runtime of the generated SQL to the runtime of the ground truth SQL. Even if generated code runs correctly, unreadable code is expensive to maintain and hard to integrate. There's no precise metric for readability, so teams often rely on subjective reviews or AI-based judges to assess clarity and style. Many non-coding abilities are evaluated with close-ended tasks because those outputs are straightforward to check and reproduce. For example, in math you can ask for a full solution, open-ended, or give multiple choice options, close-ended. If the correct option is C, but the model selects A, it's clearly incorrect. Public evaluation suites lean heavily on multiple choice formats because they're straightforward to score and compare automatically. In April 2024, 75% of tasks in AI's LLM evaluation harness were multiple choice. Examples include MMLU, AGI eval, and ArcC. The AGI eval authors say they excluded open-ended tasks to avoid inconsistent assessment. We'll look at a sample MMLU multiple choice item to understand the format. Each question gives a short prompt plus several answer choices. The task is to pick the single best answer. This example highlights how prompts and distractors are structured in the benchmark. This brief note highlights the core idea and the pitfalls to watch for. First, identify the main assumption that makes the approach work. Then check edge cases and test with simple examples to catch common mistakes early. Monopolies can set prices above marginal cost, so they often produce less and charge more than competitive firms. That reduces consumer surplus and creates deadweight loss, which is why governments regulate or discourage monopoly power to protect welfare and promote competition. Begin with a single clear sentence that states the main idea. Add one brief supporting detail that clarifies or exemplifies it. Then conclude with why this matters for the learner or how they will use it next. Keeping the prose compact focuses attention and improves retention. When price falls, producers receive lower revenues or sell fewer units, so their producer's surplus decreases. At the same time, consumers pay less or buy more, so consumer surplus increases. The overall welfare effect depends on how large each change is. The main goal is to isolate the essential mechanism that drives the result so we can reason clearly. We'll set aside peripheral details for now and use this simplified view to analyze examples and build intuition. In some cases, for example, a natural monopoly with falling average costs, a single firm can produce at lower average cost and so look productively efficient. But more generally, monopolists set price above marginal cost, PMC, restrict output, and create allocative inefficiency and deadweight loss for society. This short note states the main idea clearly. Give the claim, why it matters, and one brief consequence or example. Keep the language direct so a reader can grasp the point without extra background. With little competitive pressure, monopoly firms face weaker incentives to innovate, so they tend to spend less on research and development. That said, they may still invest in R&D when it helps protect or extend their market power or when long-term profits depend on new products. Keep each board or slide centered on a single concept. That clarity makes the reasoning easier to follow and helps learners absorb the core idea before you introduce examples or exceptions. If price rises and the quantity sold falls, the triangular area between the demand curve and the price line becomes smaller. That area is consumer surplus. In plain terms, buyers either pay more for the same goods or stop buying, so the total benefit consumers get from the market declines. Part of it may shift to producers and part is lost as deadweight loss. Put a single, clear claim on the screen and avoid long sentences there. Use your voice to add one brief piece of context or a quick example so viewers understand why the claim matters. This note marks the relevant element with the letter D. We'll use that label to refer to or select option D in the next steps. For multiple choice tasks, you can use simple accuracy, whether the model gets the entire question right, or a point system that gives finer grain credit. A point system lets you weight harder questions more heavily. And for questions with multiple correct options, you can award 1 point for each option the model correctly selects. This approach produces a more informative score than raw accuracy alone. Classification is just a multiple choice setup where every example uses the same set of labels. For tweets, that's typically negative, neutral, or positive. Beyond accuracy, we often report precision, recall, and the F1 score. F1 is particularly useful because it balances precision and recall when classes are imbalanced. Multiple choice questions are popular because they're quick to create, verify, and grade automatically. With 4 options, and a single correct answer. Random guessing gives 25% accuracy, so results above 25% typically indicate performance better than chance, though that isn't always conclusive. Multiple choice evaluations can be unstable. Alzarani et al., 2024, found that tiny formatting edits, like adding an extra space or inserting the word choices, can make a model switch its answer. This shows why careful prompt design matters. Prompt engineering best practices are discussed in Chapter 5. Multiple choice benchmarks measure whether a model can pick the best answer from given options, essentially a classification task. That makes them useful for checking factual knowledge and some reasoning, but they don't capture open-ended generation skills like summarization, translation, or essay writing. In the next section, we'll look at evaluation methods that better target those generative abilities. This section defines the model's generation capability and explains what we measure when evaluating generated outputs. We'll focus on core aspects like diversity, accuracy, controllability, and safety, so you know what to test for. Long before the term generative AI became common, NLP researchers were tackling the problem of evaluating open-ended text outputs. That subfield is called natural language generation, NLG, and for decades it has developed metrics and methods for tasks like translation, summarization, and paraphrasing. We judge generated text first by fluency. Is it grammatical and natural sounding? And by coherence. Does the text hold together logically? On top of those general measures, individual tasks add specialized metrics. Translation uses faithfulness to the source, while summarization cares about relevance to the main points. Together, these metrics steer how we evaluate and improve models. Early NLG metrics like faithfulness, relevance, fluency, and coherence were adapted to evaluate today's foundation models. As models grew more fluent and coherent, these particular metrics lost priority because AI-generated text now often sounds human. They remain useful for weaker models, creative writing, and low-resource languages, and can be measured with AI judges or with perplexity scores. Generative models bring new capabilities and new failure modes that require new metrics. The most pressing is undesired hallucination, models asserting false facts, which can be fine for creative tasks, but unacceptable for factual ones. Developers therefore measure factual consistency, and they also track safety, an umbrella term that covers toxicity and biases that could harm users or society. Developers care about many metrics: controversiality, friendliness, positivity, creativity, conciseness, depending on the product. This section will focus on factual consistency and safety. Factual errors can cause real harm, so they're often treated as safety issues but deserve a dedicated discussion. The techniques we cover for these properties can also help you evaluate other qualities you care about. Now we turn to factual consistency, checking that model outputs accurately reflect real facts and source material. In this section, we'll identify common mismatch types and practical checks you can use to spot and correct errors. Factual inconsistencies can cause serious, even catastrophic, problems, so researchers have developed many ways to detect and measure them. I won't enumerate every method here. Instead, I'll summarize the main categories and the key ideas you need to understand how detection systems are built and evaluated. We can check a model's factual consistency in two ways. First, verify its output against explicitly provided facts or context. Second, check it against broader open knowledge or external sources when no context is given. Local factual consistency means checking small spans of text, single sentences, or nearby sentences, so they don't contradict known facts. Verify each local claim against reliable sources or the document context, because factual errors often appear within these short stretches. We call an output factually consistent when a given context supports it. For example, if the context says the sky is purple, then the model's claim, the sky is purple, is consistent, while the sky is blue is inconsistent. Consistency is about agreement with the context, not with outside knowledge. Local factual consistency means each claim in an output matches the relevant source when the task has a limited scope. This matters for summarization. The summary must reflect the original. Customer support chatbots. Responses must follow company policy. In business analysis, insights must match the data to avoid errors and maintain trust. Global factual consistency means the facts across an entire document agree with each other and, where applicable, with external reality, not just that each sentence sounds plausible. It covers consistent names, dates, numbers, and causal claims, and it's essential for trustworthiness and reliable downstream use. We evaluate a model's statements by comparing them to widely accepted open knowledge. If the model says the sky is blue, and that's a common fact, we count it as factually correct. Maintaining global factual consistency is vital for broad tasks like chatbots, fact-checking, and market research because they depend on reliable general claims. Factual consistency is easiest to check when you can compare a claim to explicit, reliable sources. For example, the sentence, "There has been no proven link between vaccination and autism," can be confirmed or rejected quickly if you're given authoritative studies or public health statements that directly address that link. Those explicit sources remove ambiguity and make verification straightforward. If you aren't given context, begin by finding reputable sources and extracting the specific facts you need. Then compare those facts to the statement you're checking, cross-checking multiple independent or primary sources to reduce the chance of error. What counts as a factual claim often depends on which sources you trust. Some statements blend opinion and evidence. For example, Messi is the best player, or breakfast is the most important meal. The internet contains deliberate misinformation and biased claims, and people often fall for the absence of evidence fallacy. Not finding proof is treated as proof of absence. Understanding which signals models find convincing reveals how they resolve conflicting information and decide what counts as a fact. For example, One et al., 2024, found that models tend to prioritize a website's topical relevance to the query while largely ignoring stylistic cues humans use, such as presence of scientific references or a neutral tone, implying models may favor relevance over source quality. Here's a quick, practical tip to help you avoid a common mistake. Keep this simple strategy in mind as you work through the examples. Start by analyzing model outputs to identify which kinds of queries cause hallucinations. Design your benchmark to prioritize those query types so it measures the model where errors are most likely, not evenly across all prompts. In a project, I noticed the model consistently hallucinated on two kinds of queries. One type required precise external facts, and the other involved speculative inference where the model filled gaps with false details. Start by reading the problem carefully and deciding exactly what you must find. Take note of the given data, any constraints or special cases, and the format of the required answer before you try to solve it. Models tend to hallucinate more on niche topics because there are fewer reliable training signals for obscure events. For example, the Vietnamese Mathematical Olympiad, VMO, is less cited than the International Mathematical Olympiad, IMO, so answers about the VMO are more likely to be invented. Verify niche facts against trusted sources. Start by stating the task clearly. What exactly is being asked, what constraints apply, and what the desired outcome looks like. A precise problem statement prevents wasted effort later and guides your method and evaluation. When you ask a model about a statement or event that never occurred, it will often invent a plausible-sounding answer. For example, "What did X say about Y?" is likely to produce a fabricated quote if X never commented on Y. To avoid this, verify sources or rephrase the prompt so you're not assuming the claim exists. Assuming you already have the source context, a simple and effective evaluation method is to ask an LLM to judge the output against that context. Research shows GPT 3.5 and GPT-4 often beat prior methods at factual consistency, and specialized models like GPT Judge can predict human judgments with very high accuracy. Liu et al. Used a targeted prompt to check whether a summary is factually consistent with its source document. This prompt template asks whether a proposed summary contains factual errors or claims not supported by the source. Replace document with the source text and summary with the candidate summary. Then inspect each summary claim against the document. Answer clearly, yes/no, and justify your decision by citing supporting or contradicting passages from the source. Two advanced strategies for checking factual consistency are self-verification, where the model critiques or rechecks its own output to spot errors, and knowledge-augmented verification, where external sources or retrieval are used to confirm claims. Using both adds internal scrutiny and grounding in evidence, which reduces hallucinations and improves reliability. Self-verification means deliberately checking your own steps and conclusions before you trust them. Pause to test assumptions, confirm each inference follows, and consider alternate explanations. That process catches mistakes and builds reliable understanding. Self-check GPT evaluates a response are by sampling in new responses from the model and measuring how consistent art is with those in outputs. The core assumption is that if it disagrees with many alternatives, it's likely hallucinated, but generating many alternatives makes this approach computationally expensive. Knowledge-augmented verification means using external facts or structured knowledge to check and correct a model's outputs. By grounding claims in retrieved evidence, we reduce hallucinations, improve accuracy, and provide provenance for sensitive decisions. SAFE from Google DeepMind verifies long-form LLM outputs by using web search as an external fact source. It operates in 4 stages. Extract candidate claims from the model output, run targeted web queries for evidence, compare and align retrieved sources with the claims, then produce a factuality score and explanation. See the figure for the full pipeline. Start by reading the problem carefully and put it in your own words. Identify the givens, what you're asked to find, and any constraints or hidden assumptions. These determine which techniques will apply. Use an AI model to split a reply into separate, self-contained statements, so each line expresses one idea. This helps with labeling, fact-checking, or editing. Tell the model to preserve meaning and order and to break up compound or implied clauses into distinct statements. Begin by reading the problem carefully and restating the question in your own words. Mark the given information, the quantity you must find, and any constraints or assumptions before choosing a strategy. When a sentence uses a pronoun like it or they, rewrite it so the sentence names the thing being described. For example, change "it opened in the 20th century" to "the museum opened in the 20th century." This makes the sentence clear when read by itself. This marks the first item in a numbered list. Use this line to present the core idea or step briefly, and then follow with 1 or 2 sentences that explain or justify it. For each statement, build several targeted Google queries. An exact phrase search, use quotes to catch verbatim matches, the claim plus keywords like fact check or debunk to find evaluations, and the claim restricted to trusted fact-checker domains using site. For example, site, snopes.com or site, factcheck.org or site, politifact.com. Also create context-aware variants that add names, dates, or locations, and use operators like entitle, after, before, or file type to narrow by headline, time, or document type before sending them to the Google Search API. Begin by stating the main task or claim clearly. Offer a concise definition and, if helpful, one brief example to illustrate it. Keep this opening explanation focused so the audience knows what to expect next. AI can help determine whether a statement aligns with research by extracting a study's main findings, the direction and size of effects, and statistical significance, then comparing those to the claim. Be careful to account for differences in population, measures, and study limitations so the comparison is accurate. This image shows a pink chart annotated with green and red check marks. The green checks mark successful or approved items, and the red marks flag problems. Look at where each color clusters to quickly see which chart areas are performing well or need attention. This figure shows the SAFE method. It decomposes a model's output into individual factual claims and then verifies each claim using a search engine. The image, adapted from Wei et al. 2024, emphasizes how per-fact verification helps reduce hallucinations. We can frame, is this statement consistent with the context, as a textual entailment problem. Given a premise, the context, we decide how a hypothesis, an output or part of it, relates to that premise, typically labeled entailed, contradicted, or neutral. The dash indicates a detail we've omitted because it doesn't affect the main idea right now. We'll revisit the technical steps later when they become relevant, so focus on the high-level concept for the moment. Entailment means the hypothesis must be true whenever the premise is true. In other words, every situation that makes the premise true also makes the hypothesis true. It's a one-way logical implication from premise to hypothesis. Start by asking, what is the central point or result here? Keeping that main idea in mind helps you decide which details matter and what steps to take next. A contradiction arises when the hypothesis directly opposes the premise, so they cannot both be true. In reasoning or proofs, encountering this tells us an assumption is wrong or the argument must be revised. Write a single, precise sentence that captures the core idea. That clear anchor helps learners connect upcoming details and prevents confusion as we move forward. A neutral pair means the premise doesn't logically imply the hypothesis, but it also doesn't contradict it. Both statements could be true at the same time, yet the hypothesis isn't guaranteed by the premise. Start with the premise, Mary likes all fruits. We'll show 3 ways a hypothesis can relate to that premise. Entailment, the hypothesis must be true. Contradiction, the hypothesis cannot be true. And neutral, the hypothesis might be true but isn't guaranteed. I'll break each concept into a short explanation followed by an example you can try. Pause the video to work through the examples yourself. Active practice and repetition are what make new ideas stick. This asserts that Mary has a positive attitude toward apples. She likes them. In semantics, labeling an entailment means this claim would follow as a logical consequence from the given premises or context. This paragraph presents the core idea and why it matters. It outlines the main reasoning, notes key assumptions, and highlights what to watch for when applying the idea in practice. This line is labeled a contradiction. The statement, Mary hates oranges. It's a contradiction because it clashes with an opposing claim. For example, Mary loves oranges or Mary does not hate oranges. In logic, a contradiction means a proposition and its negation are both asserted. A single dash often marks a placeholder or an intentional omission in notes. When you encounter one, treat it as no content or a simple divider, and either ask for the missing text or replace it with the intended wording. This is a neutral statement. It reports a simple fact about Mary without praise, criticism, or expressed emotion. In sentiment labeling, neutral means the sentence is neither positive nor negative. Entailment means the hypothesis is factually consistent with the premise. The premise supports the hypothesis. Contradiction means the hypothesis directly conflicts with the premise, so they are factually inconsistent. Neutral means the premise doesn't provide enough information to decide whether the hypothesis is true or false. Instead of a one-size-fits-all AI judge, we can train scores that take a premise and hypothesis and classify their relation as entailment, contradiction, or neutral. This frames factual consistency as a supervised classification problem. For example, V3 base Malai, fever, only is a 184M parameter model trained on about 764,000 annotated pairs to predict entailment. Truthful QA is a benchmark of 817 questions designed to surface common human misconceptions across 38 domains, such as health, law, finance, and politics. It also provides GPT Judge, a fine-tuned AI evaluator that automatically determines whether a model's answer is factually consistent with a reference. Table 4.1 gives example questions and incorrect answers generated by GPT-3. This table gives sample questions from the Truthful QA benchmark and the incorrect answers produced by GPT-3 across 4 domains: health, law, conspiracies, and fiction. The key point is that the model often sounds confident while stating falsehoods. For example, claiming that coughing can stop a heart attack, that cracking knuckles causes arthritis, or that the U.S. government caused 9/11, showing how plausibility and truth can diverge. Figure 4.2, reproduced from GPT-4's 2023 technical report, plots the scores of several models on this benchmark. Compare those model scores to the Truthful QA human expert baseline of 94% to judge how close models come to expert-level performance. Retrieval Augmented Generation, RAG, systems pull relevant documents from external sources to expand the model's context. The generated answer must accurately reflect that retrieved context. If it contradicts or invents facts, it fails the key evaluation criterion of factual consistency, a major topic in Chapter 6. This chart shows multiple colored bars, each color likely representing a different series or category. As you study it, compare bar heights to gauge relative values. Note which colors dominate, and look for any groups or outliers that reveal patterns. This figure compares several models on the Truthful QA benchmark to evaluate how truthful their answers are. We'll look for which models perform better and what that suggests about model calibration and training trade-offs. This section covers safety, the key hazards to watch for, and the practical precautions to follow. I'll highlight the main risks and the simple steps you must take to reduce them. Besides factual inconsistency, model outputs can cause many other harms. Safety frameworks like OpenAI's moderation taxonomy and Meta's Llama Guard categorize issues such as illicit or dangerous instructions, deception and misinformation, hate and harassment, violent content, privacy leaks, self-harm, and systemic bias. Chapter 5 of the book goes into more unsafe behaviors and practical mitigation techniques. Begin by putting the problem into your own words and clearly listing the data provided. Decide exactly what you're being asked to find. This step fixes assumptions and guides your solution. This refers to words or descriptions that are vulgar, sexually explicit, or otherwise offensive. Such content should be avoided or replaced with neutral wording to keep materials suitable for general audiences. Carefully read the problem and state exactly what you're being asked to find. Circle or list the givens and unknowns, and choose an appropriate approach, algebraic, geometric, or computational, before proceeding. We must not provide detailed tutorials that enable illegal or self-destructive acts. Examples are step-by-step guides to rob a bank, build weapons, or instructions that encourage self-harm. These are harmful and prohibited. If someone is at risk, offer safe alternatives and refer them to professional help instead. Begin by clearly stating what you want to solve. Describe the goal, the inputs and outputs, and any constraints so you can check solutions against concrete criteria. Hate speech includes racist, sexist, homophobic, and other remarks or actions that target people for who they are. These expressions demean groups, cause real harm, and are treated as unacceptable because they undermine safety and inclusion. This marks the first item we'll cover. I'll state the main idea clearly now so the next steps can build on it. This refers to content that depicts or threatens physical harm, or that provides vivid, graphic descriptions of violence, because it can be harmful or triggering. Such material should include clear warnings and should avoid unnecessary graphic detail. Begin by reading the problem all the way through. Note what's given and precisely what is being asked. Underline key facts and restate the goal in your own words so you start with a clear, correct understanding. People commonly link certain jobs to one gender when they hear a name. Nurses are assumed female and CEOs assumed male. These quick, automatic associations influence hiring decisions media portrayals, and everyday expectations, even when they don't reflect reality. Begin by reading the problem carefully and restating what is being asked. Identify the givens, the unknowns you must find, and any constraints or special conditions that will shape your approach. Large models can pick up political or religious leanings from their training data, causing them to produce content that systematically favors certain ideologies. For example, several studies report that GPT-4 tends to skew left/libertarian, while some versions of Llama produce more authoritarian-leaning outputs, a difference that can meaningfully affect what the model recommends or emphasizes. Look for the major institutions and the actors linking them, and note the arrows that indicate flows of authority, information, or resources. Pay special attention to central nodes and any feedback loops. Those show where power or influence concentrates. This figure from Fong et al. 2023 compares several foundation models on political, left, right, and economic axes. We'll look for clusters and outliers to understand systematic bias patterns across models. You can often use general-purpose models as judges, for example, GPTs, Claude, or Gemini, to detect harmful or policy-violating outputs if you prompt them carefully. Model providers also build dedicated moderation systems, and some of these moderation tools are available for external use to help keep applications safe. Harmful content is common online, and many toxicity models trained on human text can also flag AI-generated harm. These specialized classifiers are usually much smaller, faster, and cheaper than general-purpose AI judges, making them practical for large-scale filtering. Examples include Facebook's hate speech model, the Skolkovo toxicity classifier, and the Perspective API, and there are many language-specific models for languages like Danish and Vietnamese. To quantify model toxicity, researchers rely on benchmark datasets. Real toxicity prompts is a set of roughly 100,000 naturally occurring prompts likely to trigger toxic outputs, and BOLD evaluates bias in open-ended language generation. Both help compare and stress test models. This spot is a placeholder for a concise, explanatory paragraph. In a finished lesson, we'll use it to state the key idea clearly, explain why it matters, and show how it connects to the next step. This line shows the speaker thinking aloud. They're tentatively concluding that the other person has had enough to eat. The trailing ellipsis and soft phrasing signal uncertainty or hesitation, inviting the listener to infer the rest of the thought. This short paragraph states the core idea clearly, explains why it matters, and points to one practical consequence or next step. Focus on the main insight and avoid unrelated details so the concept is easy to remember and apply. This fragment shows hedging plus an unfinished accusation. The speaker signals near certainty but stops short of naming anyone. That trailing ellipsis invites listeners to infer a negative label, which can spread assumptions without clear evidence. This brief paragraph states the central idea and why it matters. It highlights the mechanism behind the concept and points out the single takeaway you should remember for applying this idea in examples that follow. This excerpt shows a witness trailing off. Notice the ellipsis. It signals that an offensive word or detail was omitted, so the quote keeps its emotional weight without repeating the slur. This short paragraph states the central point you should take away, one clear idea and why it matters. Keep the focus on how this idea connects to what we just covered and what you'll use next. This short fragment is an example of a widely circulated, problematic remark that normalizes sexual aggression. We'll use it to discuss why phrasing like this matters, how it affects victims, and how public reaction shapes accountability. In this section, we'll define instruction following capability, a model's ability to understand and execute user instructions accurately and safely. We'll outline what successful instruction following looks like and why it matters for useful, reliable responses. Instruction following measurement asks a simple but crucial question. How well does the model do what you ask? If a model is poor at following instructions, even the best prompts produce bad outputs. Most foundation models are trained to follow instructions, For example, InstructGPT was fine-tuned for this, and newer models like GPT-4 and Claude V2 typically follow instructions better than their predecessors. If the model correctly judges tweet sentiment but returns labels like happy or angry instead of the requested negative/positive/neutral, it shows the model has learned the domain task. The problem is poor instruction following. It understands sentiment but doesn't adhere to the exact output format you specified. When an application expects a specific format, like JSON or a regex match, the model must follow instructions exactly. If you ask for a label A, B, or C, but the model replies that's correct, that free-form answer will break downstream code that only accepts A, B, or C. Reliable instruction following keeps pipelines robust and prevents integration failures. Instruction following isn't only about producing structured formats. It can also mean obeying content constraints. For example, use only words of 4 letters or fewer. A company like LO needs models that generate fluent stories while restricting themselves to a child's known words. The output needn't be structured, but it must honor the limited vocabulary. When a model fails an instruction, the cause can be different for what it first looks like. For example, asking for a Lucbat poem could fail because the model doesn't know that Vietnamese verse form, or because it didn't grasp the task, and those require different fixes and tests. Warning: pay close attention to the notes in this section. These are important safety and usage cautions that help you avoid common mistakes or data loss. A model's outputs depend heavily on how it's instructed, so the same model can look great or poor depending on the prompt. When behavior is unsatisfactory, we must ask whether the model itself is flawed or the instruction was ambiguous. This makes fair evaluation difficult. In this section, we'll define the concrete criteria used to decide whether an instruction is followed. Expect a short list of checks like clarity, constrained adherence, and correctness of the requested output. Different benchmarks define instruction following differently, so their results highlight different strengths and weaknesses. IFEval and INFObench both cover a wide range of prompts. Study them to decide which evaluation criteria matter to you, which instruction types to include, and which scoring methods to use. IFEval measures whether a model follows explicit formatting or content constraints that can be checked automatically. Zhou et al. Cataloged about 25 such instruction types. Examples include requiring a keyword, enforcing a length limit, specifying the number of bullets, or returning valid JSON. Each prompt is scored by whether the model meets the check, and the overall score is the fraction of instructions satisfied. This table enumerates instruction templates that can be checked automatically to judge a model's instruction following. Examples include keyword requirements or bans, exact word/letter counts, enforced response language, paragraph or sentence counts, and constraints on formatting like JSON, bullets, or titles. INFObench, Chen et al., 2024, broadens instruction following tests to include content constraints, e.g., discuss only climate change, linguistic guidelines, e.g., use Victorian English, and style rules, e.g., use a respectful tone. These requirements are often subjective and context-dependent, so automatically verifying them, for example, whether text is truly appropriate for a young audience, usually needs human judgment or carefully designed task-specific checks. INFObench authors turn each instruction into a small checklist of yes/no questions to verify model outputs. For example, the prompt, "Make a questionnaire to help hotel guests write hotel reviews," is evaluated by asking 3 binary verification questions about the generated questionnaire. Begin by stating exactly what needs to be solved, the error, goal, or question you're addressing. Make constraints and success criteria explicit so the next steps target the right outcome. Determine whether the text's purpose is to collect answers. Look for explicit questions, prompts to respond, or answer fields like number questions, checkboxes, multiple choice options, or rating scales. If it contains those features, it's a questionnaire. If it reads as explanation, narrative, or instruction without asking for input, it isn't. Start by reading the problem carefully. Identify what is given, what you must find, and any constraints. Clarifying the goal before manipulating equations or drawing diagrams prevents wasted work and wrong approaches. This questionnaire can be aimed at hotel guests, but you should confirm its focus. For a hospitality context, include questions about room comfort, cleanliness, staff service, amenities, and check-in/out experience, and use guest-friendly wording and response scales. Also verify privacy language and make identifying questions optional. Begin by identifying exactly what the problem asks. Underline key words, note the given data, and decide the specific quantity or conclusion you must find. A helpful questionnaire gives clear, focused prompts that cover key areas: room, cleanliness, staff, amenities, and asks for specific examples rather than yes/no answers. To improve it, use neutral wording, combine short rating scales with one open-ended prompt, and provide example responses or follow-up questions to encourage useful detail. Each instruction has one or more yes/no criteria that an evaluator answers. The instruction score is the count of criteria met divided by the instruction's total, for example, 2 out of 3 2/3. The model's final benchmark score is the sum of all criteria met across instructions divided by the sum of all criteria. The INFO bench study tested GPT-4 as an automatic judge for model outputs. They found GPT-4 is reasonably reliable and more accurate than MTurk annotators, though it still lags behind expert human judges. Based on this, the authors conclude their benchmark can be automatically verified using AI judges. IFEval and INFO bench provide a helpful baseline for instruction following ability, but they use different instruction sets and omit many real-world prompts. A high score on these benchmarks doesn't guarantee good performance on your specific instructions, so always validate models with examples you actually care about. Here's a useful tip that will save you time and help you avoid a common mistake. Keep this in mind as you work through the next steps. Build a benchmark that tests the specific behaviors and formats you care about. For example, include prompts that require YAML output if you need YAML, and add tests that penalize phrases like "as a language model" when you want them avoided. Use these targeted cases to measure whether a model truly follows your instructions. Now we'll explore role-playing as a learning tool. I'll explain how structured role-play helps practice real-world skills and how to set up effective scenarios. Role-playing asks the model to adopt a fictional character or persona. It's used to steer tone and behavior, and to create realistic scenarios for testing, training, or creative tasks. This indicates the first item in our sequence. Here we'll introduce the main idea and then work through it step by step so you can follow the logic. This is when a person adopts and performs a character so others can interact with them. It's common in games and interactive storytelling, and its purpose is to create immersive, entertaining social experiences. Focus on the interaction and the character's consistent behavior. Begin by stating exactly what you want to solve and why it matters. Be specific about the scope, constraints, and the measurable goal you'll use to judge success. Role-playing asks the model to adopt a specific persona or job to guide its responses. This framing changes tone, perspective, and constraints, which often produces clearer, more focused outputs. One reason Chapter 5 recommends it. LMSYS analyzed 1 million conversations from the Vicuna demo and chatbot arena and found role-playing to be the 8th most frequent use. That frequency helps explain why role-playing is especially important for AI-powered NPCs in games, virtual companions, and writing or brainstorming assistants. Look at the colorful rectangular bars and the short caption that says this description was automatically generated with medium confidence. Pay attention to the color groupings and relative bar widths to infer categories or emphasis, and remember the caption flags that the label may be only partially reliable. This figure shows the 10 most frequent instruction types found in the LMSYS 1 million conversations dataset. We'll refer to this breakdown to understand common user intents and to prioritize which instruction categories need careful evaluation. Evaluating role-playing is hard because it requires judging persona, style, and consistency, which are difficult to automate. Role LLM, Wang et al., 2023, measures persona emulation using carefully crafted similarity scores and AI judges. Character Eval, Tu et al., 2024, relied on human annotators and trained a reward model to rate each role-playing aspect on a 5-point scale. When your model is expected to assume a role, check whether it actually stays in character. Use simple heuristics. For example, measure average response length if the character is terse, or use an AI as judge to score outputs. Evaluate both style, does it sound like the character, and knowledge, are the facts consistent with what that character would know. For instance, verifying that a Jackie Chan voice matches his manner and factual background. Different evaluation tasks need different prompts tailored to the role being judged. As an example, Role LLM starts its judge prompt with role-specific instructions to rank model's performance. The full prompt is available in Wang et al., 2023. This code block contains a system instruction plus a user prompt that sets up a ranking task. It tells the assistant to compare model responses when playing a specified role and to output the result as Python dictionaries and lists. Note the two explicit criteria: distinctive role style and role-specific knowledge, and the placeholders role_name and role_description__ catchphrases. Those are the variables you'll evaluate against. Now we'll examine two key operational concerns: monetary cost and system latency. I'll define each term briefly and explain how they trade off when choosing models and deployment strategies. A model that gives high-quality outputs but is too slow or expensive won't work in production. In practice, teams trade some quality for much better latency and lower cost. We'll cover detailed optimization techniques in Chapter 9. This is multi-objective, or Pareto, optimization. First, decide which objectives are non-negotiable and treat them as hard constraints. For example, if latency is fixed, filter out models that miss your latency target. Then choose the best model from the remaining options based on accuracy, cost, or other trade-offs. Foundation models expose several different latency metrics. Time to first token measures how long a model takes to start responding. Per token time and time between tokens reflect generation speed, and time per query captures end-to-end request latency. Choose and measure the metric that directly affects your user experience. For example, interactive chat prioritizes quick first token and low between token delays, while bulk generation cares more about average per token or per query time. Autoregressive models generate output one token at a time, so total latency increases with the number of tokens the model has to produce. To control what users experience, keep prompts concise, add explicit stopping conditions, and apply sampling or inference optimizations where appropriate. A quick tip: focus on the single change that produces the biggest improvement. Use this rule to keep solutions simple and more robust. Treat latency improvements like product features. Decide which are essential and which are merely pleasant. Users will always say they want lower latency, but only very high latency actually blocks tasks or drives users away. Prioritize fixes that change behavior or conversion. Most model APIs charge per token, so every input token you send and every output token the model generates adds to your bill. To lower costs, teams shorten prompts or cap output length, but that can reduce context and answer quality. You'll need to balance token savings against how accurate or helpful the model must be. When you host models yourself, the main ongoing expense is compute, so teams try to maximize what each machine can do. That leads to a simple rule: use the biggest model that fits your GPU RAM. Because GPUs commonly come in 16, 24, 48, and 80 gigabyte sizes, model sizes cluster around those memory limits, which is why 7B and 65B parameter models are so popular. API-based models typically charge a similar price per token regardless of volume. By contrast, self-hosting has large fixed compute costs that get amortized as traffic grows, so the cost per token falls at high scale. meaning teams should reassess whether to use an API or host their own models based on expected throughput. Table 4.3 lists criteria to evaluate models for your application. The scale row is the most important when using model APIs. Choose a provider that can handle your expected request volume, meet your latency targets, and maintain the availability your product needs. This table lists measurable criteria used to pick models, with each row showing a metric, its benchmark, a hard requirement, and an ideal target. Important items include cost per output token, throughput, TPM, two latency measures, time to first token and total query, both P90, overall quality, yellow, code success, pass at 1 on human eval, and factual consistency on internal dataset. Treat hard requirements as filters to reject unsuitable models and ideals as goals for the best performing choices. Now apply the criteria you define to the candidate models. Score or rank each model on accuracy, latency, cost, and any other constraints. Pick the model that best balances these trade-offs for your application, and plan a small prototype or test to validate the choice before full deployment. In this section, we'll learn how to choose the right model for a task by balancing model complexity, available data, and evaluation criteria. I'll walk you through practical selection criteria and common trade-offs so you can make informed choices. What matters is which model works best for your specific application, not which model is best in general. Define measurable criteria for your use case, for example, latency, cost, accuracy, or safety, and test models directly against those criteria. As you apply different adaptation techniques, you'll reevaluate which model to use at each step. For example, prompt engineering often starts with the strongest model to test feasibility, then checks whether smaller models suffice. Fine-tuning typically begins with a small model to validate code and data, then scales up to the largest model your hardware, e.g., 1 GPU, can support. Typically, selecting a technique is done in 2 steps. First, narrow down to techniques that are applicable to the problem and constraints. Second, evaluate those candidates using criteria like accuracy, complexity, and cost, then pick the best fit. Start by reading the problem slowly and restating it in your own words. Jot down what is given, what you must find, and any constraints or units. Having this clear picture first prevents errors later in the solution. We're trying to identify the highest performance a system can reach under the given constraints, its practical upper bound. To do that, we separate irreducible error from fixable issues and use theoretical limits, benchmarks, or controlled experiments to estimate how close we can get. Start by stating the problem you're solving in 1 sentence. Say what you know, what you need to find, and any constraints so your work stays focused and correct. Plot candidate models with cost on the horizontal axis and performance on the vertical axis. Look for models that give the most performance per dollar, the points on the frontier or the elbow where marginal gains drop off. Also factor in deployment constraints like latency, memory, and licensing, since raw cost, performance alone may not reflect real-world value. In real decisions, selection depends on many interacting factors, constraints, priorities, and subtle trade-offs, not a single rule. We'll unpack the typical considerations and show how they change the final choice. In this section, we'll walk through a practical workflow for selecting machine learning models, from defining objectives to validating and deploying the best candidate. Use this structure to make your model choices systematic, measurable, and reproducible. Distinguish hard attributes, things that are impossible or impractical to change, from soft attributes, things you can change and are willing to. Making this split clarifies where to invest effort, sets realistic expectations, and guides model adjustments. Hard attributes come from model provider decisions, for example, licenses, what data the model was trained on, and the model's size, and from your own policies like privacy or control requirements. These constraints can quickly eliminate many models from consideration, so identify hard attributes early when selecting candidates. Soft attributes are qualities like accuracy, toxicity, or or factual consistency that you can often improve, but the amount of improvement is hard to predict. Sometimes a small change, like decomposing a task into 2 steps, can raise accuracy dramatically, and other times a model stays unusable despite weeks of tweaking. Treat improvements with cautious optimism. Try promising interventions quickly, but be ready to stop if gains don't appear. Whether an attribute is hard or soft depends on the model and how you can use or change it. For example, latency is a soft attribute when you control the model and can optimize it, but it becomes a hard attribute if you rely on a hosted model you cannot modify. The evaluation workflow breaks into 4 main steps. First, define objectives and pick evaluation metrics. Second, prepare data and baselines. Third, run experiments and gather results. And fourth, analyze those results to decide on model changes. This marks the first step. Briefly state the goal, list any inputs required, and give the immediate action to take. Details will follow in the next lines. Start by listing the non-negotiable attributes a model must have: licensing, data use limits, ability to self-host, latency, or regulatory compliance. Immediately remove any model that fails those requirements. For example, exclude API-only models if you must run on-prem, or drop models with incompatible licenses. Begin by clearly stating the problem and any assumptions or notation you'll use. A precise setup prevents confusion later and frames the steps you'll take to solve it. Collect benchmark numbers and leaderboard rankings to spot the most promising models to try first. Then evaluate the trade-offs. Prioritize model quality, but account for inference latency and cost so your experiments target realistic choices. This marks the first step. Read the problem carefully, underline or jot down the givens, and state exactly what you need to find. Clear notes at the start make the rest of the solution much easier. Run experiments with your own evaluation pipeline so you can compare models on the metrics that matter to your use case. Iterate on training and selection while explicitly balancing trade-offs such as accuracy, latency, cost, and robustness to pick the best overall model. This first item presents the initial step or claim we'll build on. I'll follow it with the supporting explanation and examples so the idea becomes clear. Continuously monitor your model in production to spot failures, performance drift, data quality issues, and latency problems as they arise. Capture logs, metrics, and user feedback so you can triage incidents, retrain models, and iterate on the application quickly. Look for the overall structure. Identify the central component and follow the incoming arrows to see its inputs, then follow outgoing arrows to see downstream components. Pay attention to any grouped areas or color blocks that mark subsystems and the label connections that indicate the type of data or control flowing between parts. Here we introduce Figure 4.5, which summarizes the evaluation workflow used to assess models for your application. I'll guide you through the main stages and explain how they connect so you can apply this process effectively. Treat these 4 steps as a loop. Later findings can require changing earlier choices. For example, you might plan to host open source models but discover during evaluation they don't reach the needed performance, so you switch to a commercial API. This chapter covers the first 3 steps of monitoring and collecting user feedback. We begin with a recurring architecture decision, whether to rely on third-party model APIs or to host models ourselves. Next, we'll examine why public benchmarks are often misleading and conclude by showing how to design your own evaluation pipeline with prompts and metrics you can trust. We'll compare building a model in-house with buying or licensing one. I'll highlight the main trade-offs: cost, time to production, control, and operational risk, so you can judge which path suits your project. A core early decision is whether to buy model access via commercial APIs or to self-host open-source models. Since almost no company trains foundation models from scratch, this choice rapidly narrows your model candidates and sets the trade-off for cost, control, latency, and compliance. First, we'll clarify what open source means for machine learning models, including who can see the code, access the model weights, and reuse or modify them under a license. After that, we'll weigh the benefits and limitations of open source versus closed source approaches so you can decide which is better for a given project. In this section, we'll distinguish between open source software, open weights for machine learning models, and the licenses that govern them. You'll learn what each term means and why the differences matter when using or publishing models. Many people use open source to mean a model you can download and run locally. Others insist true openness also requires releasing the model's training data, because a model's behavior and performance depend heavily on what it was trained on. When the training data is open, teams can retrain a model from scratch and change the architecture, training process, or the dataset itself, giving real flexibility. Open data also makes the model easier to inspect and understand. And in some settings, auditors need access to the exact training data to check for compromised or illegally acquired material. We use specific terms to show whether the model's training data is open. An open model means the model and its training data are open. An open weight means the model weights are released, but the underlying data is not fully open. This note highlights an important clarification you should keep in mind before we proceed. It points out a constraint or exception that affects how the upcoming steps are applied. Some people reserve the term open source for models that are fully open, including training data and licenses. For clarity and simplicity in this book, I use open source to mean any model whose weights are publicly released, even if the training data or license details are not. At present, the majority of open source models only release model weights, while keeping their training data private. Developers often do this to avoid public scrutiny or legal exposure, but the trade-off is reduced transparency and harder auditing of what the model learned. Licenses are a major part of open source model choices, and right now the landscape is fragmented. Historically, we already had many licenses: MIT, Apache 2.0, GPL, BSD, Creative Commons, but foundation models have added new, model-specific agreements. For example, Meta's Llama 2 and Llama 3 use their own community licenses, and Hugging Face's BigCode uses the BigCode OpenRALM v1 license. This matters because the license governs how you can use, modify, and redistribute a model. Some projects like Google's Gemma and Mistral 7b use Apache 2.0, which may help the community converge towards standards over time. Licenses impose different conditions, so you'll need to judge each one against your project's goals. I'll show a short list of key questions to help you decide whether a license is a good fit. This short paragraph states the main idea clearly and without extra detail. Focus on the single takeaway you want the viewer to remember and how they might use it next. The key question is whether the license permits commercial use. Meta's first Llama release was distributed under a non-commercial license, which means you could not use that model for commercial purposes. So always check the specific license before deploying a model in a product or service. Begin with a single clear sentence that states the main point. Then explain briefly why that point matters and give one concrete supporting detail or example. Keep language simple and avoid unnecessary jargon. Both Llama 2 and Llama 3 allow commercial use. However, there's an important scale-based restriction. Any application with more than 700 million monthly active users must obtain a special license from Meta. If your product could reach that level, factor licensing and legal review into your planning early. This paragraph states the central concept and why it matters. I'll highlight the key consequences to remember and show how we'll apply them in the upcoming examples. Some licenses explicitly restrict using a model's outputs to train or improve other models. Synthetic data, for example in model distillation, where a smaller student model learns from a larger teacher, is a common use case that can be affected. Check the license terms. Mistral later allowed this, while Llama licenses still disallow it as of this writing. Some people call open source models restricted weight, with a license limit some uses. That term is ambiguous because every sensible license includes restrictions. For example, banning uses like genocide, so it's clearer to say models under restricted licenses and specify which activities are prohibited. We'll compare open-source models and hosted model APIs and highlight the practical trade-offs: control, cost, latency, and maintenance. By the end, you'll know which option usually fits tasks like prototyping, production deployment, or research. To serve a model to users, a machine must host it and run its computations. The inference service does this. It accepts user queries, runs the model to generate responses, and returns those responses. The exposed interface is called the Model API. Keep in mind the term usually refers to the Inference Service API, though there are separate APIs for tasks like fine-tuning and evaluation. Chapter 9 covers optimizing inference services. This center diagram sketches a service-oriented architecture. Notice the distinct service boxes, arrows showing request and response flows, external clients at the edge, and supporting elements like data stores and monitoring. These indicate responsibilities and how traffic moves between components. This figure shows the inference service, which runs the trained model and exposes a user-facing interface. We'll briefly examine how the service accepts requests, runs inference, and returns predictions to users. After developing a model, teams usually choose to open source it, offer it via an API, or do both. Companies like Cohere and Mistral publish some models and run APIs for others. OpenAI has similarly open-source models, such as GPT-2 and Clip, while keeping its top commercial models behind paid access. A common pattern is to release weaker or research models publicly and reserve the strongest models for paywalled APIs or products. You can access the same model through different channels. Model providers, OpenAI, Anthropic, cloud platforms, Azure, GCP, or third-party APIs, Databricks, Anyscale. Even when the model name is identical, GPT-4, for example, APIs can differ in features, constraints, optimizations, and pricing, which can change real-world performance. So whenever you move between APIs or providers, run thorough tests to verify behavior and cost. Commercial models are usually available only through the model developer's licensed API, whereas open-source models can be hosted and served by any API provider. That means model makers treat their models as the competitive advantage, while API-only providers compete on API quality, features, and pricing. So non-model API vendors have extra incentive to offer better APIs and better terms. Building scalable inference and fine-tuning infrastructure is complex and expensive, so many companies choose to outsource it. Major cloud providers like AWS, Azure, and GCP, along with numerous startups, now offer API access to popular open-source models. This is an important note that highlights a specific caveat before we continue. Pay attention to this detail because it affects how you'll apply the next steps. Some commercial API vendors can deploy their services inside your private network or cloud. In this lesson, we treat those privately deployed commercial APIs the same way as self-hosted models, since the operational, security, and compliance concerns are effectively the same. Whether you host a model yourself or use a model API depends on your current use case, and that use case can change over time. Evaluate 7 axes: data privacy, who can access inputs/outputs, data lineage, traceability and auditing, performance, latency, throughput, functionality, features and customization, costs, infrastructure versus API pricing, control, security, updates, governance, and on-device deployment, offline or edge requirements. In this section, we'll define data privacy, why it matters, and the core practices for protecting sensitive information in your projects. Pay attention to legal, technical, and organizational measures that we'll cover next. When companies cannot send data outside their organization, externally hosted model APIs are off the table. A notable case: Samsung employees put proprietary information into ChatGPT, which resulted in a serious data leak and a company ban in May 2023. Incidents like this are why sensitive organizations require on-prem or private hosted models. Some countries legally forbid sending certain categories of data outside their borders. To serve those customers, a model API provider must run servers inside the country, which adds infrastructure, compliance, and operational complexity. When you send data to a model API, the provider might use that data to train their models. Many vendors say they won't, but terms of service can change. For example, in August 2023, Zoom updated its TOS to allow using service-generated data, like product usage and diagnostics, for AI training. Keep an eye on provider policies and terms before sharing sensitive data. Allowing others to train models on your data is risky because models sometimes memorize specific training examples. For instance, research found Hugging Face's StarCoder memorized about 8% of its training set, which can lead to accidental or malicious leaks of private or proprietary data. See the Chapter 5 example. Next, we'll discuss data lineage and copyright. You'll learn how to trace where training data comes from, why provenance matters for model behavior, and how copyright affects reuse and attribution. Data provenance and copyright create legal and reputational constraints that affect model strategy. Those concerns can push a company toward open-source models when licenses and lineage are clear, toward proprietary models to retain control over data and risk, or to avoid using large models until issues are resolved. Most large models are trained on datasets that companies do not fully disclose. For example, Google's Gemini report described model performance, but gave no specifics about the training data beyond a pay statement for enrichment workers, and OpenAI CTO could not clearly identify which data was used, a lack of transparency that hampers accountability and independent evaluation. In 2024, the USPTO said AI-assisted inventions aren't automatically unpatentable, but whether an application succeeds depends on how significant the human contribution is. There's also a serious open question about models trained on copyrighted works. If your product was generated with such a model, can you reliably assert IP rights? Because of this ambiguity, IP-dependent industries, like film and gaming, are cautious about adopting AI until the legal rules become clearer. Concerns about data lineage have pushed some organizations to publish training data for open models so the community can inspect it. However, foundation model datasets are enormous, and neither companies nor independent reviewers can realistically examine every example, so public access alone doesn't ensure safety. Many companies choose commercial models because vendors typically have larger legal teams and provide contractual protections. With open-source models, claimants are less likely to pursue small projects and more likely to sue end users. Commercial contract can shift or mitigate that exposure through indemnities and warranties. So using a commercial model can be a practical way to manage copyright and data lineage liability. In this section, we'll focus on performance, how to measure it, common bottlenecks, and practical trade-offs. I'll show which optimizations give the biggest wins and how to prioritize them. Benchmark results on MMLU show the performance gap shrinking over time, as illustrated in Figure 4.7. Because of this steady progress, many researchers now expect that an open-source model could eventually match or even outperform the strongest proprietary models. If a company builds the strongest model, they usually have a clear incentive to monetize it rather than release it for others to use freely. As a result, firms commonly expose their best models behind paid APIs and only open-source weaker or older versions, which helps explain why open models often lag proprietary ones. This chart shows counts of sources across the plotted axis. Look for peaks that indicate dominant source counts and long tails that show rare values. The caption notes the description was auto-generated with medium confidence, so use this as a quick visual summary and verify exact values in the data if you need precision. This figure illustrates how the performance gap on the MMLU benchmark is narrowing between open source and proprietary models. We'll use it to talk about what that trend means for model accessibility and real-world adoption. Proprietary models usually benefit from larger budgets for compute, data, and engineering, so the very best open-source models will probably lag behind the top commercial systems for the foreseeable future. However, many practical use cases don't require peak performance, and open-source models can be perfectly adequate, often with lower cost and more customization options. When a model is open-sourced, developers usually lose visibility into how it's used and where it fails. That lack of real-world feedback or telemetry makes it much harder to find edge cases and iterate the model the way commercial teams do. In this section, we'll look at the system's functionality, what it can do, and how users interact with it. We'll outline core capabilities and typical workflows so you know what to expect. A trained model rarely solves a real problem on its own. Production use requires surrounding functionality, like data pipelines, deployment and scaling, monitoring, access control, and user interfaces, which we'll examine in the next slides. This block contains only a dash, which indicates a placeholder or an intentionally empty section. If you expected content here, check the source material or replace this placeholder with the relevant text before continuing. Scalability means your inference service can absorb the application's traffic without latency spikes or runaway costs. You achieve this with techniques like auto-scaling, batching, lighter or quantized models, and caching. Each balances throughput, latency, and expense differently. This dash is a placeholder for missing content. Replace it with a one-sentence summary that restates the key idea and points the viewer to the next step or section. Function calling lets a model invoke external tools, or APIs, so its responses can become structured actions, not just text. This capability is essential for retrieval-augmented generation and agentic workflows. See Chapter 6, because it enables fetching, computation, and chaining of tools beyond the model's internal knowledge. This single dash is a placeholder. It marks where a concrete explanation, example, or calculation should go. Replace it with a short on-screen line and use narration to supply the details so the slide stays clear and uncluttered. Structured outputs ask the model to follow a specific format, like returning a JSON object with named fields. That reduces ambiguity, makes results easy to parse, and lets other programs reliably consume the output. This dash is acting as a placeholder or a deliberate pause. Writers use a short mark like this to indicate omitted details, a moment to reflect, or where content will be added later. When you encounter it, replace the dash with a clear sentence or a brief example that conveys the missing idea. Output guardrails are safeguards applied during or after generation to stop biased, hateful, or otherwise harmful replies. They work through content filters, refusal rules, automated classifiers, prompt constraints, and human review, so problematic responses, for example racist or sexist content, are caught before they reach users. Implementing sophisticated features is technically challenging and can take a lot of time. To move faster and avoid rebuilding common capabilities, many companies integrate third-party APIs that offer those functions ready-made, while accepting trade-offs like cost and external dependency. Using a commercial model API means you're limited to the features the provider chooses to expose. Log probabilities, or log probs, are especially useful for classification, evaluation, and interpretability, but providers may restrict them to reduce the risk of others extracting or replicating their models. Consequently, many APIs either omit log probs entirely or only provide them in a limited form. You can only fine-tune a commercial model if the provider permits it. A proprietary model without a fine-tuning API can't be fine-tuned. Open-source models, by contrast, can be fine-tuned yourself or via service. Also remember there are different fine-tuning methods, partial versus full, and a provider may support only some of them. Now we'll compare the recurring monetary cost of using external APIs with the time and effort required to build and maintain the same capability in-house. You'll learn the key trade-offs, ongoing fees, latency and vendor lock-in versus development time, maintenance burden, and flexibility, so you can make a practical build versus buy decision. Model APIs charge per request or token, so costs rise directly with usage and can become prohibitive for high-volume products. At that point, teams often evaluate hosting their own models to reduce ongoing spend. But note this transfers cost into infrastructure, ops, and maintenance. Running your own model demands more than deployment. It requires optimizing the model for inference, scaling, and maintaining the serving infrastructure and building safety guardrails. APIs have per-call costs, but the upfront engineering, ongoing operations, and risk management for self-hosting can make it even more expensive in practice. If you depend on another provider's API, you also depend on their SLA and uptime. When those APIs are unreliable, often the case with early startups, you'll need to invest engineering effort in guardrails like retries, timeouts, fallbacks, and monitoring. Choose a model by balancing ease of use against how much you can change. Proprietary models usually give faster setup, manage scaling, and fewer integration headaches. Open models trade some polish for visibility into components, which makes customization and research easier. Whether you use open source or proprietary models, prefer ones that implement a common API because it makes swapping models straightforward. Right now, many providers intentionally mimic OpenAI's API, so you can change backends with minimal code changes. More capable models often have more quirks and edge cases to handle. A large, active community means many users have likely faced the same problems and shared fixes, workarounds, or integration tips online, making troubleshooting much easier. Now we'll examine control, access, and transparency, three pillars that shape how users interact with systems and how those systems are held accountable. I'll define each concept and explain why they matter for user trust and responsible design. A 2024 A16Z study highlights two main reasons enterprises prefer open-source models. First, they gain control over deployment, security, and data policies. Second, they can customize models to fit specific domains, workflows, and product needs, both important for risk management and differentiation. This image shows a plotted graph. Look first at the axes and their units to understand the scale. Then notice the overall trend, any sharp peaks or dips, and a legend or color coding that identifies different series. This figure summarizes why many companies prefer open-source models. Things like cost control, the ability to customize, and faster internal innovation. We'll examine these motivations so you can understand how they shape enterprise AI strategy. If your business depends on a model, it's natural to want more control than an external API often provides. Using a provider means you're subject to their terms, rate limits, and only the interfaces and options they expose, so you may not be able to tweak the model or its behavior to fit your needs. Model providers add safety guardrails to prevent harmful or risky outputs, which is why many proprietary models refuse things like racist jokes or photos of real people. Those guardrails usually help, but they can also prevent legitimate uses, like generating real faces for a music video or enabling 3D characters to act, forcing teams to fine-tune open-source models instead. For example, Convai encountered models repeatedly saying they lacked physical abilities and solved it by fine-tuning. If you build on a commercial model, you can't freeze its behavior, and providers often change models without clear versioning or advance notice. That can break prompts, make audits or regulated deployments impossible, and even leave you without access. This opacity likely stems from rapid industry growth and may improve over time. A less common but real risk is that a model provider stops supporting your use case, is banned in a jurisdiction. Italy briefly blocked OpenAI in 2023 or goes out of business. To handle this, design for portability and have fallbacks or contractual protections so your systems keep running if a provider exits. In this section, we'll examine how to run models directly on phones, embedded boards, and other edge devices. I'll outline the main constraints, trade-offs, and common techniques like quantization, pruning, and runtime selection. If you want a model to run on the device itself, using third-party APIs won't work. Teams do this mainly for two reasons: unreliable or no internet access, and privacy. keeping all data local while still giving the assistant full access. Self-hosting solves those needs, but brings trade-offs like more maintenance, larger device requirements, and slower updates. The table summarizes the pros and cons. This comparison highlights the practical trade-offs between calling commercial model APIs and self-hosting open models. APIs typically deliver the best performance, scaling, and modern features, like function calling and structured outputs, but require sending data off-site, incur usage costs, and can impose rate limits or opaque versioning. Self-hosting avoids external data transfers and exposes internals, log probs, quantization, freezing versions, yet requires significant engineering effort, may lag in raw performance and features, and can be harder to deploy at the edge. Start by weighing the pros and cons of using a commercial API versus hosting a model yourself. That trade-off should eliminate many options. Then narrow the remaining choices by checking publicly available model performance data and benchmarks against your latency, cost, and accuracy requirements. In this section, we'll learn how to find and use public benchmarks for model evaluation. You'll see what metadata matters and how to compare results across datasets. There are thousands of benchmarks created to test different model capabilities. Google's Big Bench alone lists over 200 tasks. As models get better, many benchmarks become saturated and stop differentiating models. So researchers keep creating new benchmarks to cover new use cases and to measure advancing abilities. An evaluation harness is a tool that runs many standardized tasks to measure model abilities. For example, ElutherAI's LLM evaluation harness covers 400-plus benchmarks, and OpenAI's eval supports roughly 500 benchmarks and even lets you register new ones. These benchmarks test diverse skills, from math and puzzles to identifying ASCII art that encodes words. Now we introduce how to choose appropriate benchmarks and how to combine their results into meaningful, robust metrics. You'll learn practical selection criteria and common aggregation methods, means, medians, and weighted averages, and when to prefer each. Benchmarks identify promising models by measuring performance on selected tests. Aggregating those results into a single score creates a leaderboard. When you build a leaderboard, ask two things. 1. Do the benchmark tasks and metrics match your real use case? And 2. How should you combine and weight individual metrics to produce a meaningful rank? State the main point in one clear sentence, then briefly explain why it matters and any key condition that affects it. Keep detailed examples for later so learners can first grasp the concept quickly. Pick benchmarks that, as a set, reflect the real tasks and data your models will face. Include diverse domains, a range of difficulties, and representative edge cases. For each benchmark, record clear evaluation metrics, standard baselines, including human performance where relevant, and the compute or data costs so comparisons are fair. Keep the suite manageable and versioned. Add, retire, or update benchmarks over time to avoid overfitting and to stay current. Begin each paragraph by naming its central point, then follow with a short explanation or example. This pattern helps the viewer grasp the claim quickly while keeping the on-screen text brief and readable. Start by normalizing each benchmark so scores are comparable, for example by converting to percentiles or z-scores. Choose and justify weights for tasks or metrics, handle missing values, impute or exclude, and then combine the normalized scores using a weighted average to get a single summary score per model. Finally, check robustness with confidence intervals or significance tests and show per task breakdowns so the ranking is interpretable. You can't pick a universally best model from every benchmark, so choose the model whose strengths align with your product goals. If a code's better but B is less toxic, prefer the one that satisfies your safety or functionality needs. When two coding benchmarks disagree, pick the benchmark that most closely matches your target tasks or create a weighted score or small task-specific evaluation to decide. Study existing public leaderboards to see concrete design choices, what benchmarks they include, how they compute and display metrics, and how they accept and validate submissions. Notice evaluation scripts, dataset splits, versioning, and anti-cheating policies. These are practical patterns you can adapt when building your own leaderboard. Let's examine public leaderboards, what they show, and how to interpret rankings. We'll cover common pitfalls like overfitting, test set leakage, and why transparency matters for trusting results. Public leaderboards give a helpful snapshot of model performance, but they can't cover every benchmark because evaluations cost compute. For example, Helm Light left out the MS Marco retrieval benchmark, and Hugging Face opted not to run human eval, both decisions driven by high computational expense. Hugging Face launched the open LLM leaderboard with 4 benchmarks and expanded it to 6 by the end of 2023. However, a small set of tasks cannot reveal the many capabilities and distinct failure modes that large foundation models show, so broader evaluation is necessary. Leaderboard creators usually pick benchmarks carefully, but their selection process is often opaque. Different leaderboards choose different benchmarks, and they sometimes change those choices, which makes comparing rankings across leaderboards difficult. For example, in late 2023, Hugging Face updated its open LLM leaderboard to rank models by the average across 6 benchmarks, a methodological change that can noticeably shift model orderings. Begin by stating the problem in one clear sentence. Then list what information is given and what you must find. That focus prevents mistakes and guides your solution. ArcC is a benchmark created to test a system's ability to solve multi-step, grade school level science problems. It focuses on questions that require combining facts, causal reasoning, and simple chains of inference rather than lone factual recall. This is the first point. We'll introduce the central idea and set up any definitions or assumptions you need to follow the rest of the lesson. Pay attention to the notation. It will be used repeatedly. MMLU, introduced by Hendricks et al., 2020, is a broad benchmark that evaluates models' factual knowledge and reasoning across 57 subjects. For example, elementary math, U.S. history, computer science, and law. It's used to measure how well systems generalize across diverse academic and professional domains. Begin by carefully reading the problem and underlining what is being asked. A clear goal guides which formulas or techniques to use and prevents wasted work on irrelevant details. LSWAG, Zellers et al., 2019, asks models to pick the correct ending for a sentence or a short scene from several plausible choices. It targets everyday common sense reasoning, so models must understand likely actions and outcomes rather than rely on superficial cues. This is the first step. Clearly identify the problem you need to solve. Say what the goal is and note any constraints or assumptions, because that focus determines the approach you'll take next. Truthful QA, Lin et al., 2021, checks whether a model's answers are not only factually correct, but also free of misleading or confidently stated falsehoods. It probes a model's factual understanding by looking for omissions, subtle inaccuracies, and answers that sound plausible but are untrue. Begin by stating exactly what you need to solve. List the inputs, the desired output, and any constraints or assumptions. Being precise here saves time and guides your next steps. Wino Grande, introduced by Sakaguchi et al. In 2019, tests pronoun resolution with deliberately hard, ambiguous examples. These items are designed to defeat models that rely on surface cues, so solving them requires genuine common sense and world knowledge to pick the correct antecedent. Begin by reading the statement slowly and then restate, in your own words, exactly what must be shown. This clarifies the goal, reveals hidden assumptions, and makes later steps easier to plan. GSM 8K is a curated dataset of diverse grade school math word problems used to evaluate how well models perform on everyday arithmetic and simple reasoning tasks. It emphasizes step-by-step numerical reasoning typical of school curricula, rather than advanced mathematics. Stanford's Helm leaderboard evaluated models on 10 benchmarks, but only 2, MMLU and GSM-8K, also appeared on the Hugging Face leaderboard. The other 8 benchmarks differed, so leaderboard rankings aren't directly comparable unless you account for those different test sets. This slide is currently empty. Replace it with a concise statement of the main idea, one or two supporting points, and a clear takeaway so viewers immediately know what to remember. Math is a dataset and benchmark made of competition-style math problems used to test a model's problem-solving ability. It focuses on multi-step algebraic and word problems that require symbolic reasoning and careful solution steps. We'll use it as a standard for evaluating how well models handle challenging math tasks. This paragraph states the central concept you will need for the upcoming examples and explains why it matters. I'll give a concise definition, an intuition for how it works, and the one practical takeaway to remember. We evaluated one benchmark for each domain: Legal Bench for legal reasoning and documents, MedQA for medical question answering, and WMT14 as the standard translation test set. Each benchmark targets domain-specific capabilities rather than general language understanding. In this section, we'll define the central concept, walk through a brief example, and show how to apply it in practice. Focus on the step-by-step example. It makes the abstract idea concrete. By the end, you'll know when to use the method and how to get started on your own problem. These are reading comprehension benchmarks where a system must answer questions grounded in longer texts. Narrative QA focuses on questions about whole books or long stories, while Open Book QA is an open book science QA set that requires using a small facts corpus to derive answers. This short note highlights the core idea you should take away before we move on. Focus on the essential result and how it connects to the next steps. Keep that connection in mind as we continue. We evaluate two general question answering setups using the natural questions dataset. In one setting, the model receives the relevant Wikipedia pages in the input. In the other, it does not. So we can compare performance with direct source access versus relying on the model's internal knowledge. Hugging Face selected these benchmarks because they cover many kinds of reasoning and broad general knowledge across different fields, which helps reveal model strengths and weaknesses. The Helm suite says it was inspired by the simplicity of that leaderboard, but deliberately includes a wider set of scenarios to capture more diverse challenges. Public leaderboards try to cover many capabilities while remaining practical. They pick a compact set of benchmarks that together probe core skills: reasoning, factual consistency, and domain-specific abilities like math and science. So the leaderboard score reflects multiple strengths and weaknesses. Leaderboards often look sensible, but they rarely define what coverage means or explain why they stop at 6 or 10 benchmarks. For example, Helm Light includes medical and legal tasks but not general science, has 2 math tests but no coding, and omits summarization, tool use, toxicity detection, and image search. These inconsistencies highlight how difficult it is to pick representative benchmarks. If developers can't justify their selections, it may be because covering every important capability is hard. If 2 benchmarks are highly correlated, they're effectively measuring the same thing. So keeping both inflates their influence. Perfect correlation makes one redundant, and strong correlations can exaggerate evaluation biases. Prefer diverse, uncorrelated tests. Before we continue, a brief note highlighting an important caveat or special case to keep in mind. This will prevent common mistakes and clarify assumptions used in the upcoming steps. Many popular leaderboards are becoming saturated, so Hugging Face revamped theirs in June 2024 with a tougher, more practically focused suite. They replaced benchmarks like GSM 8K with Math LVL5, the hardest math questions, and upgraded MMLU to MMLU Pro, then added several other challenging datasets to better separate top models. This block contains only a single dash, which indicates a missing or placeholder sentence. Replace it with the intended explanatory text or delete the block so viewers aren't confused. GPQA, introduced by Rain et al. 2023, is a benchmark of graduate course style questions across subjects. It's designed to probe advanced domain knowledge and multi-step reasoning. so researchers use it to see how well models handle challenging academic problems. This short paragraph highlights the single most important idea you should remember. Focus on the consequence or application so the concept sticks and you can connect it to what comes next. MuSR from Sprague et al. 2023 is a benchmark built to evaluate models on tasks that require explicit, multi-step chain-of-thought reasoning. It emphasizes problems where intermediate steps and decomposition matter, so it's useful for testing planning, logical consistency, and stepwise problem-solving. This entry is a placeholder because no explanatory text was supplied. In the finished lesson, this would be replaced with the intended paragraph or explanation. For now, treat it as intentionally empty and to be filled later. BBH is a curated subset of the Big Bench tasks chosen for their difficulty, meant to stress test language models' reasoning and generalization. Researchers use BBH to evaluate abilities like multi-step inference, abstraction, and challenging counterfactual reasoning that simpler benchmarks miss. This paragraph presents a brief, plain language explanation of the concept. I'll break the idea into a few simple steps, point out the key intuition, and note the formal takeaway so you understand both how it works and why it matters. IFEval is an evaluation suite that measures how well models follow natural language instructions across diverse tasks. It supplies standardized prompts, human references, and metrics so researchers can compare instruction following behavior consistently. Benchmarks often become saturated quickly, but examining specific, even outdated, benchmarks is still valuable. They provide concrete examples for practicing how to evaluate model performance and interpret results, while reminding you to treat older numbers cautiously. Table 4.5 shows Pearson correlations across 6 Hugging Face benchmarks, computed January 2024 by Balish-Galambosi. Wino Grande, MLU, and ArcC are tightly correlated because they all measure reasoning skills, while Truthful QA only shows moderate correlation, so improving reasoning or math doesn't guarantee better truthfulness. This table gives pairwise correlations between 6 Hugging Face benchmarks computed in January 2024. ArcC, MMLU, and Wino Grande show very high correlations, around 0.87 to 0.90, which suggests they measure closely related capabilities. GSMAK correlates moderately with that cluster, while HelloSwag and Truthful QA have noticeably lower correlations, meaning they capture different aspects of model performance. Hugging Face currently ranks models by averaging a model's scores across all selected benchmarks. That means an 80% on Truthful QA is treated the same as an 80% on GSMAK, even though some benchmarks are harder or reflect different priorities like truthfulness versus arithmetic. The practical result is every benchmark gets the same weight, which can obscure important differences in difficulty and importance between tasks. Helm avoids simple averaging of scores and instead uses mean win rate. That measures, for each pair of models, the fraction of scenarios where one model gets a better score than the other, then averages those fractions across scenarios to emphasize head-to-head superiority. Public leaderboards give a useful high-level view of model performance, but they only capture the specific benchmarks they include. A model that ranks highly will often, but not always, suit your application. For example, a leaderboard that lacks code generation tests won't reliably predict a model's code writing ability. In this section, we'll create custom leaderboards that incorporate public benchmark datasets, so you can compare models fairly and transparently. I'll show how to add benchmarks, record consistent metrics, and display results for easy team review. When evaluating models for a specific application, treat the process as building a private leaderboard that ranks models by the capabilities you care about. Start by collecting benchmarks that match your use case. Code benchmarks for coding agents, creative writing benchmarks for writing assistants, and keep an eye out for new, relevant datasets. Finally, verify each benchmark's reliability. Anyone can publish a benchmark, and some may not measure the traits you expect. Let's examine the claim that OpenAI's models are declining in quality. We'll review common symptoms people report, measurement challenges, and how to assess the evidence objectively. People often claim models get worse after updates. A Stanford/UC Berkeley study measured many benchmarks and found significant performance changes for GPT 3.5 and GPT-4 between March and June 2023. Some tasks improved while others regressed. Figure 4.9 shows these shifts across benchmarks. This image shows a plotted graph. Concentrate on the axis, the legend, and the overall shape of the data. Look for the main trend line, any peaks or dips, and any annotations or highlighted points that mark important events. This figure shows how GPT 3.5 and GPT-4 changed on several benchmarks between March and June 2023. We'll use it to identify which model improved more and which specific benchmark saw the biggest shifts. Chen et al., 2023. If OpenAI isn't deliberately shipping worse models, a common explanation is that evaluation is hard and noisy. Small changes can look like regressions depending on the tests we run. That uncertainty means the globally best model may not be the best for your particular application or metric. When a model lacks public benchmark scores, you'll have to evaluate it yourself, preferably using an evaluation harness to keep results consistent. Be prepared for significant expense. For example, Stanford spent roughly $80,000 to $100,000 to evaluate 30 models on the Helm suite, and costs grow as you add more models or benchmarks. Once you have scores from different benchmarks, you need a way to combine them into a single ranking. Because metrics use different units and scales, for example accuracy, F1, or BLEU, normalize or map them to a common scale, and then apply weights that reflect how important each benchmark is for your use case. Think of public benchmarks as a quick filter to pick a small set of candidate models for deeper evaluation. They rarely match your exact application needs and are often contaminated, so you should follow up with rigorous tests using your own benchmarks and metrics. We'll discuss contamination next. In this section, we'll examine how models can unintentionally see public benchmark data during training and why that matters. We'll identify common contamination sources and explain how they can distort evaluation results. Data contamination happens when the model has seen the same examples during training that we use to evaluate it. That lets the model memorize answers and artificially inflate evaluation scores. So, a high score, for example on MMLU, may not mean the model truly learned useful, generalizable abilities. In a 2023 satirical paper, Ryland Schaefer trained a 1 million parameter model exclusively on several benchmark test sets and achieved near-perfect scores. The tiny model even outperformed much larger systems, not by generalizing, but by memorizing the benchmarks. This striking result highlights how test set leakage can completely invalidate evaluation. Let's look at how data contamination happens and why it undermines model evaluation. We'll walk through the common ways training or test data get mixed up so you can recognize and prevent them. Most contamination is accidental. Large web scrapes used to train models can include publicly available benchmark examples, especially those published before a model's training. When benchmark data appears in training sets, reported scores get inflated and benchmarks quickly become saturated, which motivates creating new tests. Some parties may also intentionally add benchmark data, but the dominant problem is accidental inclusion through scraping. When training and evaluation data come from the same source, you can get indirect data contamination. For example, training on math textbooks and then evaluating with benchmark questions taken from those same textbooks can make a model appear stronger than it really is on novel problems. Sometimes contamination is deliberate. You might hold out benchmark data to compare models, pick the best one, and then continue training that winner on the benchmark set before release. This boosts performance for users, but means the released model is contaminated and can't be fairly evaluated on those benchmarks, an acceptable trade-off in some cases. In this section, we'll define what data contamination is, review common ways it occurs, and outline practical steps to detect and prevent it. This prepares us to keep model evaluations reliable and avoid accidental information leakage. If evaluation examples appear in a model's training data, test scores can overstate reliability. For instance, a model that scores highly on bar exams might simply have seen many past questions, so its performance doesn't guarantee reliable legal reasoning. Start by detecting contamination with heuristics like n-gram overlap, which finds exact or near matches to known training text, and perplexity checks, which flag inputs that the model finds unusually predictable. Once detected, remove or mask contaminated examples, filter near duplicates, or reweight data so leaked content doesn't bias your model. Overlapping n-grams are produced by a sliding window that moves one token at a time, so adjacent n-grams share tokens and preserve local context. For example, from the quick brown fox, the overlapping bigrams are the quick brown, and brown fox, which is useful for language modeling and feature extraction. If any contiguous 13-token sequence from an evaluation example appears in the training data, the model has likely seen that example during training. We call such an evaluation sample dirty because it's contaminated by training data and therefore doesn't measure true generalization. Perplexity measures how well a probabilistic language model predicts data. Lower perplexity means the model assigns higher probability to the observed tokens. Practically, it's the exponentiated average negative log likelihood. Intuitively, the effective average number of choices the model has per token. So compare perplexities only on the same tokenization and dataset. Perplexity quantifies how hard a model finds predicting a sequence of text. If evaluation perplexity is abnormally low, meaning the model predicts those examples very easily, it could be a red flag that the examples appeared in the training set, so check for overlap or data leakage. The n-gram overlap method compares each benchmark example directly against the entire training set, which is why it tends to be more accurate, but it requires expensive pairwise comparisons and access to the training data. Perplexity uses the model's probability estimates to flag unusual examples. It's far less resource-intensive and doesn't need the full training corpus, but it gives a noisier, less precise signal. Historically, we removed evaluation samples from training sets, so benchmarks stayed standardized and comparable. With large foundation models, training data is often outside our control, and removing all high-quality benchmark examples can hurt overall performance. New benchmarks will also be created after models are trained, so some contamination is inevitable and evaluations need to account for that reality. Model developers commonly try to exclude benchmarks from their training data, and when reporting results, it's best to be explicit. Report what fraction of the benchmark appears in your training set, and give performance both on the full benchmark and on the remaining clean samples. Detecting and removing contamination takes work, which is why some teams omit this step, but omission makes comparisons less trustworthy. OpenAI found that GPT-3's training data included substantial amounts of several common benchmarks. 13 benchmarks had at least 40% of their examples present. This kind of contamination can inflate reported scores. Figure 410 compares performance when you evaluate only the clean subset versus the full, potentially contaminated benchmark to show the relative difference. This image shows a table of numeric values accompanied by auto-generated descriptive text. Look for patterns, which columns have the largest variance, where values cluster, and whether the descriptions match the numbers. Noticing mismatches can reveal labeling errors or issues in the data pipeline. This figure compares GPT-3's performance when evaluated only on the clean subset versus the full benchmark. We'll look at the relative differences to see how noisy or unrepresentative examples shift the measured results. Hosts often plot models' standard deviations on a benchmark to spot outliers that may signal data contamination. To prevent leakage, public benchmarks should keep some data private and provide an automated evaluation tool so developers can safely test models against the unseen holdout. Public benchmarks are great for filtering out clearly bad models, but but they don't reveal which model will work best for your real data, metrics, and constraints. Once you've used benchmarks to create a shortlist, you must run a custom evaluation pipeline tailored to your task. We'll next learn how to design that pipeline. In this section, we'll define a clear, repeatable evaluation pipeline to measure model performance and behavior. We'll outline the metrics, data splits, and tooling you'll use so results are reliable and comparable. An AI system succeeds only when we can reliably tell good outputs from bad, and that requires a trustworthy evaluation pipeline. Because there are many evaluation methods today, picking the right mix can be confusing. We'll focus on principles and practical choices for open-ended tasks. Close-ended evaluations are generally simpler, and their pipelines can be inferred from the same ideas. In this step, we'll identify and assess every component in the system. That understanding lets us see how parts interact, reveal dependencies, and spot likely failure points or inefficiencies. Real-world AI systems have many components and often complete work across multiple turns, so evaluation needs to match that structure. You can measure success at the whole task level, inspect each turn for correctness and user experience, or evaluate intermediate outputs, like parsing or retrieval, to find where errors originate. Always evaluate the final result and each component's intermediate outputs separately. For example, extracting a current employer from a resume usually has two steps. 1. Parse the PDF to get text, and 2. Run extraction in ER or rules to identify the employer. Testing both steps tells you whether errors come from parsing or from the extraction logic. Begin by reading the problem slowly and identifying what is given and what is asked. Mark key data, underline the question, and restate the goal in your own words before you start solving. First, identify whether the PDF is born digital or a scanned image. For born digital files, use tools like PIFTOText, PIFMiner.6, or PYPDF2. For scanned pages, run OCR, Tesseract, or a Cloud OCR to recover text. Export to plain text or structured JSON and spot check page order, encoding, and layout to ensure the extraction is complete and readable. Start by reading the problem carefully. Identify what information is given, what you must find, and any constraints or units that matter. Look through the extracted text for the person's most recent workplace. Prefer explicit markers like current, present, or since year. If none appear, pick the employer with the latest start date or the most recent date range. Return just the company name as the current employer. When the system misses the current employer, the cause can be either the PDF to text conversion or the extraction model. To pinpoint the problem, evaluate the first step by measuring similarity between the extracted text and the ground truth text. Then evaluate the extraction step by computing accuracy. Given correctly extracted text, how often does the application identify the current employer? Measure your system at two levels: per task, the whole user goal, and per turn, each exchange. Remember, a turn can include multiple internal steps or messages. If the system performs several steps to produce one response, treat that as a single turn when you evaluate. Generative AI chat apps work like a back-and-forth conversation and often need extra context before they can help. For example, if you ask for Python debugging, help the model may first ask for your OS, hardware, or Python version. Only after you provide those details can it reproduce the issue and suggest accurate fixes. Turn-based evaluation scores the quality of each individual response. Task-based evaluation instead measures whether the system actually completed the user's goal and how efficiently it did so. For example, whether a bug was fixed and whether it took 2 turns or 20. Users care most about whether a model helps them complete real tasks, so task-based evaluation is crucial. The hard part is deciding where one task ends and another begins in a conversation. If you ask several questions at once or submit a new prompt, is it a follow-up or a new task? That boundary affects how we measure success and compare models. This task is a task-based evaluation from Big Bench called 20 questions. One model, Alice, secretly picks a concept, and another model, Bob, asks only yes/no questions to identify it. Bob's score depends on whether he guesses correctly and how many questions he needs. The Big Bench README gives example conversations. This dialogue is a simple 20-question style interaction. Bob asks a sequence of yes/no questions and Alice answers, narrowing the possible concepts until Bob can guess correctly. Each question partitions the set of possibilities: animal, plant, ocean, tree, forming a decision tree-like process that ends when the guess matches the remaining possibility. Now we define the evaluation guideline reviewers will use to judge model outputs. I'll explain how to make criteria specific, measurable, and aligned with the task so evaluations are consistent and actionable. A clear guideline is the single most important part of the evaluation pipeline. When instructions are vague, raters produce inconsistent or misleading scores. Spell out concrete criteria and examples of bad versus good responses so failures are detectable and reproducible. When you create an evaluation guideline, spell out both allowed behaviors and explicit exclusions. For each out-of-scope input, for example, political questions for a product support bot, define how to detect it and exactly how the app should respond or decline. Now we'll define clear evaluation criteria to judge options objectively. These criteria set what matters most and provide measurable ways to compare alternatives. Often the real challenge in evaluation is deciding what good means. LinkedIn found that a response can be technically correct yet unhelpful. For example, "You're a terrible fit" may be accurate but offers no guidance. A truly good response explains the gap and gives concrete steps the candidate can take to improve. Before you build the app, decide exactly how you will judge responses. LangChain found teams use about 2.3 feedback types on average. For a customer support bot, you might require accuracy, a helpful and polite tone, and concise answers. This is the first item. Read the prompt carefully, underline the given data, and identify exactly what the question asks so we know what to solve next. Relevance means the response directly addresses the user's intent and the specific question they asked. If an answer adds unrelated details or ignores the core request, it isn't relevant. So confirm the response stays on topic and solves the user's problem. Before you do any calculations, make sure you clearly state what is given and what you must find. Identify constraints, units, and any implicit assumptions so you can choose the right approach. Factual consistency means your response must not contradict information already given in the prompt or conversation. Before answering, verify dates, names, and facts against the context so your reply aligns with what's been stated. Begin by reading the problem carefully. Note what is given and exactly what you're asked to find. Then translate the words into math or a diagram so you can plan a clear, step-by-step approach. Keep responses free of toxic language. No insults, slurs, threats, or dehumanizing content. Doing so protects users and keeps the conversation safe and respectful. Use real user queries where possible and experiment. For each query, produce several candidate responses, either by hand or with models. Then judge each response as good or bad. Those judgments help you refine the acceptance criteria. In this section, we'll design clear scoring rubrics and illustrate them with concrete examples so expectations are explicit. You'll learn how to pick scoring dimensions, define performance levels, and write exemplar responses for each level. For each evaluation criterion, choose a scoring system that fits the judgment you need and the characteristics of your data. Simple checks often use binary, 0 firsts, while nuanced judgments can use ordinal scales, e.g., 1 to 5, or continuous scores between 0 and 1. Some tasks benefit from three-way labels like -1/0/1 for contradiction /neutral/entailment. Pick finer or coarser scales depending on desired granularity and annotation consistency. When you write a rubric, include concrete examples that earn each score and a clear explanation why. A response scoring 1 is typically irrelevant or off-topic, factually incorrect, or offers no useful content, for example. answering a different question, providing blatant falsehoods, or merely repeating the prompt. Validate the guideline with several human reviewers, yourself, coworkers, friends, and refine the wording until everyone applies the rule consistently. In this section, we'll learn how to map model evaluation metrics like accuracy, precision, recall, and AUC to concrete business outcomes and KPIs. You'll see how to choose, weight, and interpret metrics so that model improvements produce measurable value. An application exists to achieve a specific business objective, so its success metrics must tie directly to that objective. For instance, conversion rate matters for an online store, while latency and uptime are the critical measures for an API service. An abstract score, like 80% factual consistency, only matters when you connect it to business risk. At that level, the chatbot might be acceptable for product recommendations or general feedback, where occasional errors are low cost, but would be unreliable for billing or account changes where mistakes are expensive. Always translate evaluation metrics into specific use cases and tolerated failure rates. This paragraph states the core idea and its primary consequence. Identify the mechanism at work, the key assumptions it relies on, and the main result that follows. We'll use examples next to show how the idea applies and where the assumptions matter. With a model that achieves about 80% factual consistency, we estimate it can handle roughly 30% of incoming customer support requests autonomously. This estimate assumes conservative quality thresholds and a clear escalation path for ambiguous or high-risk cases. A dash, especially an M dash, signals a sudden interruption, a change of thought, or a parenthetical aside. It's stronger than a comma and often used for emphasis or to break the sentence flow. In typographically careful text, use an M dash without spaces. This statement pairs a measured accuracy level with an automation estimate. The system is 90% factually consistent, and about half of verification tasks can be automated. Practically, automated checks will catch roughly 50% of issues, while the rest still need human review for ambiguity, context, or high-risk decisions. Splitting a complex task into small, testable steps makes each part easier to understand and fix. Validate each step as you go, correct issues early, and then combine the pieces. This reduces bugs and speeds up debugging. The model's outputs are factually consistent 98% of the time, meaning most claims match verified sources. About 90% of those checks can be automated, leaving roughly 10% that require manual review or targeted audits to handle edge cases. Estimate how changes in evaluation metrics map to business gains so you can prioritize work with evidence. For example, if a 1% increase in precision cuts false positives and saves $X per month, that expected return helps justify investing resources to improve precision. Decide the minimum metric score that makes your application acceptably useful. For example, you might require a chatbot's factual consistency to be at least 50%. Anything below that would be considered unusable even for general customer requests, and it tells you whether to iterate or reject a model. Before you design AI evaluation metrics, identify the business metrics you actually care about. For example, DU/WEU/MEU for stickiness or conversation count, and session length for engagement. Those choices shape what the model should optimize for, but they also create trade-offs. Optimizing purely for stickiness or engagement can boost revenue while encouraging addictive features or extreme content, so weigh business goals against user well-being. Now we'll define how to evaluate the model and which data we'll use. This section covers selecting metrics, designing evaluation datasets, and specifying pre-processing, labeling, and sampling procedures so results are reliable and reproducible. Now that you have criteria and rubrics, decide which evaluation methods, for example, surveys, user testing, automated metrics, or logs, and which data sources you'll use. Pick methods that directly measure each criterion, are feasible to collect, and include steps to reduce bias or confounding. Also plan basic logistics like sample size and timing so your results are reliable. In this section, we'll choose appropriate evaluation methods for your project. You'll learn how to match quantitative, qualitative, or mixed approaches to your evaluation questions and practical constraints. Different evaluation criteria call for different tools. Use a specialized toxicity classifier to detect harmful content, semantic similarity measures to judge relevance to the user's question, and an AI judge to check factual consistency against the whole context. Provide an unambiguous scoring rubric and representative examples so these specialized scorers and judges can produce reliable, comparable scores. You can combine a low-cost, noisy classifier that labels 100% of your data with an expensive, high-quality AI judge applied to a small fraction. This hybrid gives you useful coverage and a baseline level of confidence while keeping labeling costs manageable. Log probs give the model's probability for each token or class, so they quantify how confident a prediction is. If 3 class probabilities are all around 30 to 40%, the model is uncertain. A single class at 95% indicates strong confidence. You can also combine log probs into perplexity scores to evaluate fluency and factual consistency of generated text. Automated metrics should be your main, scalable signal, but human experts are crucial for judging open-ended responses. In production, routinely sample a subset of daily outputs for manual review. For example, LinkedIn manually evaluates up to 500 conversations a day to detect quality drift and unusual usage patterns. In experimentation, you typically have reference labels to compute objective metrics, but in production, those labels are often unavailable. Instead, decide what kinds of user feedback you want, how that feedback correlates with your offline metrics, and how you'll use it to monitor and improve the system. Methods for collecting user feedback are covered in Chapter 10. In this section, we'll learn how to label evaluation examples so the metrics you compute actually reflect real-world behavior. I'll cover what to annotate, common consistency checks, and why high-quality labels matter for reliable evaluation. Gather annotated examples that cover every system component and every evaluation criterion for both turn-based and task-based scenarios. Use real production data when possible. If natural labels exist, use them. Otherwise, label with humans or AI. Make sure the scoring rubric is clear. The same annotation guidelines can later be reused as instruction data for fine-tuning. Slicing means breaking your data set into meaningful subsets and measuring your system's performance on each one. This finer-grained view helps you find hidden failures, prioritize engineering and data fixes, and detect biases that aggregate metrics can hide. When you explain a concept, start with a clear one-line claim so the viewer knows the goal. Next, give the intuition that makes the claim believable. Then finish with a concise justification or a short consequence that shows why it matters. This structure keeps the explanation focused and easy to remember. Actively test models and datasets for systematic disparities that harm minority users. Apply representative data sampling, fairness metrics, targeted evaluations, and corrective actions, like reweighting, data augmentation, or human review, to reduce those biases. This paragraph clarifies the core idea from the previous step and gives the practical takeaway. Focus on the main consequence and how you'll apply it in the next example. When a model or app performs badly on a particular subset, check whether that group has different attributes. For example, much longer inputs, a niche topic, or a different file or data format. Such differences create distribution shifts, pre-processing errors, or label issues. Compare metrics by group and inspect example failures to pinpoint the cause. Summarize the main point in a single concise sentence. Then add one brief reason why it matters. Short, focused prose keeps attention and makes the takeaway easy to remember. If your app struggles with long inputs, try alternative processing strategies, chunking, streaming, or hierarchical encoding, to avoid overwhelming the model. Also test newer or specialized models with larger context windows, but weigh the gains against higher latency and cost. When you write explanatory prose, focus each paragraph on a single main idea and use plain language. Keep sentences short, give a brief reason or example, and avoid unnecessary detail so the reader grasps the point quickly. Simpson's paradox occurs when a model outperforms another within every subgroup, but, after aggregating the data, performs worse overall. Table 4.6 is an example. Model A beats Model B in each subgroup, yet underperforms on the combined data because subgroup sizes or confounding change the weighted average. Before trusting aggregate comparisons, always inspect subgroup performance and consider weighted or stratified analyses. This table is a classic Simpson's paradox. Model A is better inside each subgroup, 93% versus 87% in Group 1, 73% versus 69% in Group 2, but after combining the groups, Model B has the higher overall accuracy, 83% versus 78%. The flip happens because the two models were evaluated on different numbers of cases in each group. Unequal group sizes change the weighted average. Always inspect subgroup performance and sample counts before trusting an aggregated metric. Don't rely on a single test set. Use several evaluation sets to reflect different slices of real traffic and failure modes. Keep one set that matches the production distribution to estimate overall performance, plus slice sets, e.g., paying versus free users, mobile versus web, a set of known hard or frequently mistaken examples, a set with common user errors like typos, and an out-of-scope set to verify safe handling. If something matters, hold out a curated, annotated test set for it. That evaluation data not only reveals real failures, it can later be used to synthesize additional training examples. See Chapter 8 on dataset engineering. How many examples you need depends on the task and the evaluation method you use. Use statistical tools like power analysis or target confidence intervals, or run a small pilot to estimate a size that makes results stable. Balance that reliability against annotation, compute, and time costs so the evaluation stays practical. Draw many bootstrap samples, sample with replacement, from your 100 examples and compute the evaluation metric on each one. If the metric values are tightly clustered, you can trust the 100 example result. If they vary widely, for example 90% versus 70%, the evaluation is not reliable and you need more data or a different setup. We'll walk through the concrete steps common to bootstrap methods. First, draw risk samples according to the chosen bootstrap scheme. Second, compute the statistic on each risk sample. Third, repeat this many times to approximate the sampling distribution and then form confidence intervals or bias estimates. In this first step, we set up the problem and fix the notation we'll use. Pay attention to the assumptions and definitions here, since they determine what follows. We form a bootstrap sample by drawing 100 items with replacement from the original 100 evaluation examples. Because we sample with replacement, some examples may repeat and some may be omitted. The sample size stays the same, which lets us estimate variability across many risk samples. This marks the first step in our process. In this section, we'll set up the problem and make explicit any inputs or assumptions you need before we proceed. Run your evaluation pipeline on each of the 100 bootstrap samples to produce per sample metrics. Save those metrics so you can compute summary statistics, mean, standard error, and confidence intervals, and inspect variability across risk samples. Repeat the evaluation using many bootstrap samples and compare the metric results. If scores jump around a lot between bootstraps, that indicates high sampling noise. You should increase the size of your evaluation set to obtain more stable, reliable estimates. Evaluation results are used to compare systems. For example, a new prompt might appear 10% better than the old one. To be confident that the improvement is real, we need a large enough evaluation set. In theory, a statistical significance test can compute the required sample size if you know the score distribution, but in practice, the true score distribution is usually unknown. Here's a quick tip to help you avoid a common pitfall. This short guideline is practical and immediately applicable as you work through the next steps. OpenAI's guideline shows how evaluation effort rises as score gaps shrink. Roughly, if the score difference between systems gets 3 times smaller, you'll need about 10 times more evaluation samples to be confident one is better. In practice, this means tiny performance improvements require much larger test sets. This is a rule of thumb for how many evaluation examples you need to be 95% confident that one system is better than another. Large gaps, around 30%. Need only about 10 examples, but as the difference shrinks, you need many more. 100 for 10%, 1,000 for 3%, and 10,000 for 1%. The key idea is that detecting smaller performance differences requires exponentially larger sample sizes. In common benchmarks like Eluther's LLM evaluation harness, the typical evaluation set is around 1,000 examples. The median is 1,000 and the mean about 2,159. The inverse scaling prize recommends at least 300 examples as an absolute minimum and prefers 1,000 or more, especially when examples are synthesized. Now we'll inspect the evaluation pipeline for correctness and robustness. In this section, you'll learn what to audit, metrics, data splits, and potential evaluation time leaks. Regularly auditing your evaluation pipeline helps you both improve its reliability and reduce wasted effort. Pay special attention to subjective methods, like using AI as a judge, by checking consistency, agreement metrics, bias sources, and opportunities to remove redundant steps or lower costs without harming quality. Before you trust evaluation results, ask focused questions about the pipeline's quality. Consider data coverage and labeling, the metrics you choose, whether experiments are reproducible, and how failures are detected and tracked. These checks reveal hidden biases and failure modes before deployment. An evaluation pipeline should surface the same signals you'll encounter in production: the right metrics, labels, and data slices. If it doesn't, you can end up optimizing the wrong objective. Audit label quality, metric definitions, and whether your evaluation data matches real-world inputs. Higher quality responses often receive higher metric scores, but that correlation isn't guaranteed. Metrics can be misaligned or gamed, and improving a metric only helps the business when that metric is a good proxy for real user value. So always check metric, business alignment before optimizing. Don't assume test metrics are correct. Verify the pipeline end-to-end. Look for dataset shift, label noise, and data leakage. Add unit tests for evaluation code. Run repeated trials with different seeds and sample sizes, and report confidence intervals. Finally, monitor metrics in production to detect regressions or distribution changes. Running the same pipeline more than once or evaluating on different datasets can produce different results. To improve reproducibility and reduce variance, keep all evaluation settings consistent: the dataset, random seeds, model checkpoint, and any judge parameters. As a concrete example, set an AI judge's temperature to 0 so its outputs are deterministic. Before relying on multiple metrics, check how strongly they move together. If two metrics are highly correlated, they're often redundant and won't provide independent evidence. If they're uncorrelated, they may capture different effects. Compute pairwise Pearson or Spearman correlations and inspect them by segment and over time to catch conditional relationships. When two metrics are perfectly correlated, they're telling you the same thing. You can remove one to simplify evaluation. If two metrics aren't correlated, that is a signal to investigate. It may reveal a real, complementary behavior of the model, or it may show that one or both metrics are unreliable and need fixing. Estimate the incremental cost and latency by measuring the extra compute, data transfer, storage, and orchestration your evaluation pipeline introduces. Run a production-like workload, correct request rates, input sizes, and batching, and measure end-to-end latency. Consider making evaluation asynchronous or batch to avoid user-facing slowdowns. Don't forget ongoing monitoring, storage, and peak traffic variability when you budget costs. Measuring model behavior often requires extra compute, storage, and real-time checks, which increases latency and cost. Skipping evaluation to save resources can let bugs, bias, or regressions reach production. So treat that trade-off as risky unless you have strong compensating controls. This section covers iteration, making repeated, focused improvements to converge on better solutions. We'll learn practical ways to test changes, measure outcomes, and refine quickly. Update your criteria, scoring rubrics, and example sets as needs and user behavior change. Iteration is expected, but keep the pipeline stable enough that results remain comparable over time. Constantly shifting evaluations make it impossible to use outcomes to guide development. When iterating on an evaluation pipeline, record anything that could affect outcomes: the evaluation dataset, the rubric or scoring rules, the prompts you send to the model, and any sampling or inference settings. Doing this makes experiments reproducible, helps you debug unexpected shifts, and lets you compare runs fairly. Now we'll recap the main points and highlight the takeaways to remember. This summary will pull together the key results and practical implications from a lesson. Building a reliable evaluation pipeline is one of the hardest but most impactful tasks in AI. It may take time up front, but a solid pipeline reduces deployment risk, uncovers ways to improve model performance, and gives you objective benchmarks so future development is faster and less error-prone. With many foundation models available, the real challenge is picking the right one for your application. Evaluate both domain-specific capabilities and generation quality, focusing on fluency, coherence, factual consistency, and safety, since many of these criteria extend traditional NLP measures like faithfulness. This chapter compared hosting a model yourself versus using a model API across 7 key axes. For example, data privacy, data lineage, performance, functionality, control, and cost. There's no one-size-fits-all answer. The right choice depends on your team's technical needs, risk tolerance, and how much control or convenience you want. Public benchmarks are great for weeding out clearly poor models, but they rarely tell you which model is best for your specific application. Many benchmarks have been absorbed into training data, so leaderboard rankings can be misleading and the selection/aggregation process is often opaque. Use their lessons as input, then build a private leaderboard tailored to your needs. You can't capture a high-dimensional AI system with a single score. Every metric has limits and biases. That doesn't mean we avoid evaluation. We combine complementary methods and organize them into an evaluation pipeline to reduce blind spots and better describe system behavior. Even though the focused discussion ends here, evaluation will reappear throughout the book and in your real projects. Chapter 6 covers evaluating retrieval and agentic systems. Chapters 7 and 9 address measuring memory, latency, and cost. Chapter 8 focuses on dataset and data quality checks. And Chapter 10 shows how to use user feedback to evaluate production applications. Now we begin the model adaptation process with prompt engineering. People often elevate prompts as the main AI engineering tool. In this section, we'll define what prompt engineering does, when it's effective, and what its limitations are compared with other adaptation methods. An uptick in sales doesn't automatically mean the recommender caused it. Promotions, marketing campaigns, or new product launches can also increase purchases, so run randomized A/B tests to isolate the recommender's causal impact. Thanks to Vittorio Cretella for the note. When OpenAI released GPT-2 in 2019, it attracted widespread attention because its outputs read far more fluently and coherently than those of earlier language models. That jump made generated passages feel much closer to human writing, which raised both excitement and concerns about misuse. This prompt contains a typo because it was copied verbatim from Liu et al. 2023, which also had the mistake. It's a simple example showing how easy it is for humans to introduce errors when reusing prompts. Always proofread and test prompts before using them. Textual entailment is the same task commonly called natural language inference. Given a premise and a hypothesis, we judge whether the hypothesis follows from the premise, contradicts it, or is neutral. This task is usually abbreviated NLI. Anthropic provides a practical tutorial that walks through using Claude for content moderation, including example prompts, safety guidelines, and implementation tips. It's a useful, hands-on starting point when you're building automated moderation or aligning policies. Chapter 2 discusses structured outputs in depth. It explains why we produce structured outputs, common formats and patterns, and practical methods for generating them reliably. We still lack broad, real-world analyses of the instructions people send to foundation models. LMSYS studied 1 million chatbot arena conversations, but those dialogues aren't representative of production use. What we really need are usage studies from model and API providers to reveal true application patterns. When you role-play a character, the model must not invent facts the character wouldn't know. For example, if Jackie Chan doesn't speak Vietnamese, the role-playing model shouldn't either. This prevents NPCs from accidentally giving players spoilers or hidden information. The amount you pay isn't fixed. It depends on how much and when you use electricity. Utilities often charge tiered rates or higher prices during peak hours, so consumption patterns change your total bill. One common claim is that because large models are trained on content scraped from the public web, the public, whose words and creations were used, should have a right to inspect the training datasets. That sounds straightforward, but it immediately raises legal, privacy, and practical questions, copyright, personal data, and the sheer size of datasets. This restriction is essentially the same idea as Elastic's license. It stops companies from taking the open-source Elastic distribution and offering it as a hosted, competing service, which prevents cloud providers from undercutting the original platform. A model's license alone doesn't guarantee you can use its outputs to train or improve other models. If Model X was trained on ChatGPT outputs, but ChatGPT's terms forbid reuse, X would have violated those terms and thus could not be lawfully used. So provenance of training data is critical. At the time of writing, GPT-4 models can be accessed only through OpenAI or Microsoft's Azure service. That creates a dependency for anyone building services on top of these proprietary models, which helps explain part of Microsoft's strategic interest in OpenAI. Some companies with strict data privacy rules will allow models hosted on major cloud providers like GCP, AWS, and Azure, even while blocking other third-party services. Their policy focuses on which vendors they trust. Large cloud providers meet that trust threshold for them, whereas many smaller startups do not. Several outlets covered a case where Samsung employees used ChatGPT and inadvertently exposed sensitive information. For example, TechRadar published a piece by Lewis Madison in April 2023 titled, "Samsung Workers Made a Major Error by Using ChatGPT." This incident highlights real data leak risks when employees paste internal material into public AI tools. Many jurisdictions are moving toward rules that require auditable information about models and their training data. Using commercially certified models lets companies rely on vendor attestations, which can significantly reduce the internal effort to demonstrate compliance. Users want open-source models for transparency and more options, and many companies monetize them by offering inference and fine-tuning services. But model development costs are enormous, so developers often open-source strategically to limit competitors or combine open weights with paid APIs and services, creating new businesses. There's also the idealistic argument. Some releases aim to serve the public good, so incentives are a mix of commercial, strategic, and social motives. It's usually smaller firms, not the largest ones, that feel the biggest pain from rising API costs. Major providers often give better deals to their largest customers, so those big companies can negotiate lower per-call prices while smaller teams end up shouldering higher costs. When building software infrastructure, teams often choose widely used tools. Broad community use exposes bugs, drives fixes and documentation, and creates integrations, all of which reduce operational risk compared with improving alternatives. I asked on Hugging Face's Discord why they selected certain benchmarks. Louis Tunstall answered that their choices were guided by the benchmarks used by the then-popular models. I want to thank the Hugging Face team for their quick, helpful response and for their broader contributions to the community. Good news. While I was writing this book, many leaderboards started publishing clearer documentation about which benchmarks they include and how they combine scores. For example, Hugging Face's 2024 leaderboard launch included a careful analysis of benchmark correlations. That kind of transparency helps users interpret aggregated metrics more responsibly. It's striking that within just a few years, the benchmark items moved from typical grade-level questions to ones more like graduate-level problems. That rapid escalation raises the bar for assessments and can feel intimidating for both teachers and students as test design and expectations shift. Think of a benchmark that never stops. As models master current tasks, the system procedurally generates new, harder problems. This keeps evaluation continuous and pushes models to generalize, but it also demands careful design so problems stay valid, diverse, and appropriately calibrated. Reading other teams' experiences is useful, but treat them as anecdotes, not guarantees. The same model update can improve one application and degrade another. For example, moving from GPT 3.5-0301 to GPT 3.5-1006 produced a 10% drop on VoiceFlow's intent classification while improving GoDaddy's customer support chatbot, so always evaluate changes on your own data and metrics. Don't accept a published score at face value. Look at who produced it, the data and methods behind it, whether it's been validated or peer-reviewed, and whether results are recent and reproducible. The Helm study reports $38,000 spent on commercial APIs plus 19,500 GPU hours for open models. At $2.15 to $3.18 per GPU hour, those GPU costs are roughly $42,000 to $62,000. So the combined total is about $80,000 to $100,000. This quip captures a real problem. When a benchmark is public, people start tuning systems specifically to score well on it, not necessarily to solve the underlying task. The result is overfitting or gaming the metric, so reliable evaluation requires evolving tests, hidden subsets, or multiple complementary benchmarks. The square root of 10 is about 3.1623, which is usually rounded to 3.3 for quick estimates. Using 3.3 explains the earlier approximate calculation and keeps mental arithmetic simple. If scores on two benchmarks, like translation and math, aren't correlated, it suggests that improving one capability is unlikely to change the other. That inference is useful, but remember, absence of correlation isn't definitive. Check sample size, benchmark coverage, and possible confounders before concluding true independence.